Yes, ma'am. Uh, you can start, Krishika.
A very good evening to all the distinguished dignitaries, our chief guest, Professor Murlidhar Miriola, faculty members, researchers, and participants joining us today. On behalf of the North Cab University and the organizing committee, I extend a warm welcome to everyone attending this ATAL online faculty development program.
We are delighted by your presence and enthusiastic participation. This FDP brings together experts from academia, research organizations, and industry, and we look forward to a week of insightful discussions and impactful learning.
My name is Krishika.
And my name is Shivam, and we are delighted to invite you to be part of this prestigious ATAL Faculty Development Program, which brings together academia and industry experts to share knowledge, insights, and emerging perspectives in the field of semiconductor technologies. This FDP is being organized by the North Cap University, established in the year 1996 and formerly known as ITM University. The North Cap University is a progressive, multidisciplinary university located in the city center of Gurugram, Haryana. The university operates multiple schools and departments on its state-of-the-art, sustainable, and technology-driven campus.
NCU hosts a diverse student community across engineering and technology, management, liberal arts, law, applied sciences, business, media, and entertainment. Accredited with NAC Grade A, the university serves as a strong research and talent catalyst between academia and industry, delivering undergraduate, postgraduate, and doctoral programs through an immersive and industry oriented pedagogy guided by eminent academicians and industry leaders. The faculty development program is being organized under the multidisciplinary engineering department. The Department of MDE at the North Cap University offers PhD, MTech, BTech programs across core disciplines including electronics, electrical, communication, mechanical, and civil engineering.
Committed to quality education and skill development, the department focuses on industry ready training and socially relevant research. Its vision is to excel in multidisciplinary engineering through innovation, academic excellence, and globally recognized research. While its mission includes delivering top notch education, addressing industry challenges, fostering collaborations, upgrading resources, and encouraging research industry oriented projects and entrepreneurial skills through a flexible, interdisciplinary curriculum aligned with the national education policies. Aligned with MDE's vision, we now move on to the Faculty Development Program. This Faculty Development Program is a pivotal initiative in the context of India's rapidly evolving semiconductor landscape, which is poised to emerge as a global leader in chip design, manufacturing, and innovation. As India strengthens its semiconductor mission, developing a strong understanding of technologies spanning design to packaging has become essential.
FDP offers comprehensive exposure to critical areas such as clean room technologies, vacuum systems, and semiconductor fabrication processes, including lithography and etching, along with advanced topics like EDA tools, AI, and machine learning applications in VLSI and the complete design flow from RTL to GDSI.
Participants will also explore semiconductor packaging, nanomaterials, and analog and mixed signal VLSI design, gaining insights into both foundational and advanced aspects of semiconductor engineering.
Through expert led sessions on global market trends, India's semiconductor assembly and testing ecosystem, and emerging industry developments, combined with interactive discussions and practical insights, this FDP aims to strengthen research capabilities, teaching excellence, and industry collaboration, contributing meaningfully to India's vision of self reliance in semiconductors. As we continue this enlightening session, it is our privilege to invite Professor Sharda Vashish, an esteemed academician and researcher with 28 years of experience, currently serving as the head of the Department of Multidisciplinary Engineering at the North Cap University. She has been honored 7 times as the Best Teacher and Best Academic Administrator, reflecting her dedication to education.
She played a key role in establishing the navigation with Indian constellation Navik Lab with ISRO and has mentored government funded research projects with over 70 research papers, 10 patents, and a book on digital electronics and devices. She continues to drive impactful research. She also serves as Deputy Dean, International Affairs at the North Cap University, fostering global academic partnerships. We are honored to have her with us today. Ma'am, we eagerly look forward to your valuable insights.
Thank you so much. A very good evening to our chief guest, Dr. Muralidhar Miryala, Head Materials for Energy and Environmental Laboratory, Shibora Institute of Technology, Tokyo, Japan, coordinators, and all the participants. It's my privilege to extend a warm welcome to all of you at the inauguration of this AICT approved FDP on advances in semiconductor technologies from fundamentals to AI driven VLSI design and packaging. We are fortunate to have Dr. Muralidhar Miryala with us, a distinguished researcher who has received prestigious honors, including the Pravasi Bharatiya Samman Award. He has published over 500 research papers and holds multiple patents, reflecting his significant contributions to material science and global research collaboration. I'm delighted to share that this program has received an overwhelming response with more than 375 participants from across India joining us. This reflects the growing interest and commitment towards India's semiconductor mission, which aims to establish the country as a global hub for semiconductor design and manufacturing. As India takes significant strides towards self reliance in semiconductor production, the role of artificial intelligence driven VLSI design and packaging in ensuring efficiency and innovation in semiconductor fabrication becomes increasingly important. All of us can witness this nowadays. The India Semiconductor Mission is a visionary initiative that seeks to develop a robust semiconductor and display manufacturing ecosystem in the country. This mission not only aims to reduce dependence on imports, but also positions India as a key player in the global semiconductor supply chain. Advances in semiconductor technologies are transforming VLSI design and packaging through innovations spanning device fundamentals to AI driven optimization techniques. The integration of artificial intelligence, especially, is enabling faster, more efficient, and highly reliable chip design, verification, and advanced packaging solutions for next generation application. And programs like this FDP serve as important platform for capacity building and knowledge sharing. So through this as FDP, we aim to equip faculty members, researchers, and industry professionals with the latest advancements in AI-driven VLSI design and packaging. I extend my sincere gratitude to AICT, our esteemed speakers, faculty members, and organizers for their efforts in making this FDP a reality. I encourage all participants to actively engage, exchange ideas, and leverage this opportunity to strengthen their expertise in this critical domain. Together, through knowledge and collaboration, we can play our part in realizing India's ambition of becoming a global leader in semiconductor manufacturing. Wishing you all a successful and enriching learning experience. Thank you.
We sincerely thank Professor Sharda Vashish, the coordinator of this FDP, as well as Dr. Anu Tong, the co-coordinator, for their constant effort in organizing this ATAL faculty development program. It is now our proud privilege to welcome our chief guest, Professor Muralidhar Miryala, a globally recognized academician and researcher.
Professor Mirela serves as the head of the Materials for Energy and Environmental Laboratory at the Shibaura Institute of Technology, Tokyo, Japan, and his presence greatly enriches the academic stature of this FDP. Professor Muralidhar Mirela has made exceptional contributions to high temperature superconductors, functional materials, and energy efficient semiconductor technologies with over 200 international research publications, multiple patents, and widespread global recognition for his pioneering work.
Outstanding research excellence has been honored with several prestigious awards, including the Pravasi Bharatiya Samman Award conferred by the Honorable President of the Government of India in 2021. The SIT Chairman's Award in 2021, the Incredible Academician of the World Award in 2022, the Lifetime Achievement Award in High Temperature Superconductivity in 2023, and the American Telugu Association's Award of Excellence in Science and Technology in 2024. In addition, he serves as editor in chief and editorial board member of multiple international journals, reflecting his significant influence in the global research community. Now, we would like to invite Professor Muridhar Miriola to kindly share his experiences and motivate the participants.
Okay, can you hear me?
Yes, sir.
Yeah.
Yes, sir.
Okay, thank you so much. So, dear Distinguished His Excellency, Professor Nipur Prakash, Vice Chancellor, Distinguished His Excellency Professor Prem, Pro Vice Chancellor, respected Professor Sharada, Dean International Affairs, and the North Cap University team members, my dear friends, ladies and gentlemen. It is a great honor for me to be here today on the occasion of advances in semiconductor technologies, from fundamental to AI-driven VLSI design and packaging. Let me begin with the simple idea. Almost everything we use today, our mobile phones, computers, televisions, cars, and even the internet, works because of semiconductors. Semiconductors was first discovered in 19th century when scientists found that material like silicon behave neither like perfect conductor nor perfect insulator. The real revolution happened in 1947 with the invention of transistor, which replaced large and inefficient vacuum tubes. The single invention made electronics smaller, faster, cheaper, and more reliable. Over time, engineers learned how to place millions and later billions of these tiny transistors into the single chip. As a result, semiconductors became the heart of the modern technology, enabling smartphones, communication networks, artificial intelligence, and even future quantum computers. Along with semiconductors, another fascinating group of materials is the gained great attention called the high temperature superconductors, or simply we can say the high TC superconductor. These materials can carry electricity without any energy losses. Normally, when electricity flows through the wires, part of it loses its heat. But superconductor allow electricity to flow freely. What makes high TC superconductors special is that they work at relatively higher temperature using the liquid nitrogen, which is affordable and practical. These materials were discovered in 1986, and they can also produce extremely strong magnetic fields, for stronger than ordinary permanent magnets. Normally people say it's like more than 100 times. This makes them very useful for high-speed transportation, new class of medical equipment, scientific research, and future electronic technologies. One of the biggest challenges the world faces today is energy law and global warming. A large amount of electricity is wasted before it even reaches our homes. Even in advanced countries like Japan, about 5% of electricity is lost during the transmission. They may sound small, but it is equal to output of several large power plants. ITC superconductors can dramatically reduce these losses because electricity can be traveled through with them almost zero resistance. This means less energy waste, lower carbon emission, and reduced dependence of the fossil fuel. So superconducting power cables can play a major role in the future. Imagine transportation huge amount of clean electricity from the renewable sources such as solar energy from the Thar deserts in Rajasthan to cities across the India, even behind. This could be similar to how oil is distributed worldwide from the countries like Saudi Arabia or Russia. But in this case, it would be the clean and green energy. Such technology can make power grids smarter, more efficient, more reliable. So ITC superconductors can be help reduce the energy used in the data centers, facilitate and transport systems. They can make electricity motors, generators, energy storage devices, supporting electric vehicles and sustainable infrastructure. So by reducing the energy loss at every stage, these materials offer the strong path towards the energy security and climate change mitigation. Looking at the future of the semiconductor industry will increasingly depend on the dependence on the superconductors. As electric components become smaller and more powerful, problems like heat generation and power loss become the serious limitation. ITC superconductor can help overcome these limitations by enabling faster, cooler, and more energy efficient systems. They are especially important for the quantum computing, high-speed communication, and next-generation electronics. By comparing the semiconductors which control and process information with the superconductors which transmit the electricity effectively, we can build the future that the faster, cleaner, and more sustainable. Lastly, it is the great honor to acknowledge the strong communication of our Honorable Prime Minister Sri Narendra Modi ji and the Government of India in fostering the robust semiconductor ecosystem within the country. Without doubt, India holds a tremendous potential to demonstrate its strength and global leadership on the international stage. We sincerely hope that all of you will be join in this collective effort to help Indian transcend behindness of the excellence in the global race. Thank you very much for your attention.
We extend our sincere and heartfelt gratitude to Professor Birela for gracing this inaugural session and enriching it with his valuable presence and insightful address. His inspiring words, profound experience, and thoughtful perspectives have set a meaningful tone for the program and motivated all of us to engage deeply with the sessions coming ahead. Thank you all for being part of this auspicious beginning. We look forward to your continued support and engagement throughout the program.
Professor Muralidhar Miryala has made exceptional contributions to high temperature superconductors, functional materials, and energy efficient semiconductor technologies. With over 200 international research publications, multiple patents, and widespread global recognition for his pioneering work.
He will now deliver Technical Session 1, sharing insights drawn from his extensive academic and research journey. The chat box will remain open and the Q&A session will be taken at the end. With this, I extend a warm welcome and over to you, sir.
So, can I share my presentation?
Yes, sir. Just one second. Yes, sir. You should be able to share presentation.
No. There is no share option.
Are you facing difficulty, Professor Mulidhar? Hello, am I audible?
Yes, ma'am, you're audible.
I hope you have given the presenters right to sir.
Yes, ma'am, I have asked Aryan right now, and yes, he's saying that he has given the rights.
Okay.
Dear participants, we will be starting in a while. Please hold on.
Yeah, sir is joining again. He is facing some difficulty in sharing the PPT. So he's just joining. Shivam, you again can check because he has sent me the screenshot where it is written only meeting organizer and presenters can share.
Okay,
Check the
ma'am.
rights again. Yeah, check the
Yes, ma'am.
rights again.
Yes, ma'am. I'll check with Aryan right now. Just 1 second. Yes, ma'am. Aryan is giving the rights just now.
Okay.
But he actually had the rights when he tried
No,
earlier.
but he's not able to connect, and it is actually visible on his screen only.
Okay, ma'am. He's doing it again right now.
Professor Mulidhar, can you just try again? It's visible, sir. Yeah.
Okay, can you hear me?
Yes, we can hear you.
Yeah. So is it okay? Moving my screen?
Yes, moving. It's moving also.
Yeah. Okay. Thank you so much, everyone. So this is Professor Murli from the Shivara Institute of Technology. Today I am going to speak on high TC superconductor for clean energy and seeding future semiconductor technologies. So my educational background, primary focus on superconductivity and its specific phenomena, which holds the potential revolutionize various fields such as medicine, transportation, energy, and power. You can see like right-hand side figure, the levitation of magnet above the energy superconductor. Like, of course, but you can see the small one is the left and larger is the right. Left side, like the levitation of magnet is the NEG, as shown in the right, demonstrate the Messner effect. This phenomena enhances the nano-pinning media is commercially referred as the pinning effect. In the bottom figure, the is like TEM, trash mesh electron microscopy. We can make the nano pinning 40 nanometer around 1 to 3 material. As a result, and one can be levitate very heavy objectives, which was shown in the right side of the figure. So this new phenomena was attracted many like human levitation and high temperature superconductor discovery. So it is my great pleasure and honor to join the estimated group of distinguished individuals who have received the Pravasa Bharati Sanman Award, one of the India's civilian honor from the President of India. So this is the overview of my presentation. I will briefly give the introduction of the ranking systems of developed the SIT, that is like especially like QS and THE. Then I will present recent development in the superconductor technologies supported by the semiconductors and their role in the advanced zero energy future. This slide highlights the visit of the North Cap University delegation to the SIT in August 2023. It was the memorable day marked by the insightful interactions with Professor Sharda, Madam Dean of the International Affairs, and the students. Just I will be going to be talk about the first topic, like the ranking. This slide highlight the ranking developments in the SIT. When I joined SIT, there was no ranking, which was the significant drawback I highlighted the issue when the serving as the presidential advisor. Initially, many claimed that achieving the ranking at SIT is a little bit difficulty because this is not the global institute and also is like especially like Japanese research institute. However, during my tenure of the deputy president, I improved the strategic planning and systemic effort to enhance the pillars of this ranking program. As systematically, just we increased the, we can see something. I will show the more details here. So here, by like any ranking programs, they need like several pillars that like teaching, research, citation, international output, industrial income, especially in the case of QS, reputation survey, the strongly emphasize these things. Here, like to strengthen the research program, especially like when you are thinking the ranking programs, the strategies, both the quality and quantity of research and successful with this criteria is the very, very important. Increasing the number of research papers, increase the number of qualified international research staff, and to enhance the number of citations. To increase, to achieve the goals and also attract the students to SIT, we made it like several smart programs. What I've invited like so many institutions from India, like IITM, IITD, IITB, so etc. Even though some of the Amity University, Anna University, Usmania University is like even the top two ranked universities here. So here is the summary of the smart programs toward the SIT strategic goal, because we are thinking to make the top 10 technical universities in Asia in the 100 years birthday of the SIT. So here like a PhD innovative program, this has been very successful and effective in increasing the number of international peer-reviewed articles. And APBL, advanced project-based learning. This is also in APBL classroom students teams. Certainly they will work like research-based problems, and actually they will write again the research paper, which will also improve the communication skills of the students. And also with the Sakura Science Plan, this inspires the youth of the short period of time to the Japan. I hope like I think more than 20 Indian universities are invited for the last 8 years. And also international high school internship program. This is the main idea to promote the globalization in Japanese university and students. We invited local high school students to the SIT. Something like that. This more information is the already like so systematically incorporated in this book recently published, that building the global university, successful strategies and case studies. This is like of course Sakura Science program. This Sakura Science, this internet, it is the one of the major program like teaching international students the Japanese traditional culture. For to success this 2 weeks program, we designed the several like arranging the workshops for example, like a robotic workshop, lab visits, field trips, and cultural exchange, yukata workshop, the Japanese culture, Japanese tea ceremony, something like that. This is the one way we improved the international collaborations and this thing. This is the one of the most I successfully did like advanced project-based learning APBL program. This is like a simple 2 weeks program, like a research-based program, involved the collaborative research between the different universities to improve the scientific and technological visibility of SIT. The objectives are improving the diverse research collaboration, which lead to the strong and numerous publications. This is the main idea. The first, this is the example. First, this APBL was done by the 5 universities: IIT Madras, IIT Delhi from India, UPM, and KMUTT. Malaysia and Thai and SIT. This is like more than 50 students are participated, like 6 staff members. This is the one of the latter, like we did it like 5 APBL programs every year. And this is the outcome of the APBL program. You can see like several we published several papers in international journals, which plays the important role in increasing the university ranking. Then, like this is another one of the very interesting program, like PhD innovative program, because just I first pilot program I selected like example PhD students from the IIT Madras. In this case, like SIT is fully funded, their stays in SIT like say 3 months to 6 months. And in PhD students, Shibara, no, they are supposed to come and they have to work. This diversification towards the research program raised the again number of research international co-authored papers. This is like crucial for improving the ranking project. Normally, we can see like international outlook 5%. This is the combination of our partners and ours. The strong evidence of the student intellectual and collaborative across the cultural environment. They will also like this more successful. We did like 2015 to 2020, more than like 40 students are participated in this program. And also here is the again the result of the raising the international co-authored papers. What I am telling, this is the crucial for improving the all ranking projects international outlook. So I think like more than just like here the example, like just I'm showing the 23 papers. Later we published more than 12 papers. Another is like global project based learning. This like no in terms of bifurcation, students from the different cultural collaboration together solve the engineering case studies. This is the one of the example. The students from the various countries is going to participate like 2 weeks program. This is also. One can notice the international cooperation accelerated toward the excellence academic problem solving nature. We observed now more than 60 projects are going in the SIT, the APPL programs. This is the last one is the International High School Internship Program. The main idea to start this program, no, globalization of Japanese university, because ours is the purely Japanese students, interested students are very less. Then the students, no, high school students are coming to our university and working like 2 weeks. But our main idea to serve as the seed program for support the development of 100% English-based bachelor level programs at SIT. This program we are also designed so systematically, like you can see like right hand side, like welcome and introductory welcome party, laboratory activity, team building, final presentation, award ceremony, something like that. Like yeah, as you can see the next slide, like this is the example of 2019 students distributed like more than 63 students from the various countries is participated. The right side you can see US, India, Japan, South to up to Italy. Here you can see like high school students, different nations worldwide attended this program and working in the SIT's master and bachelor students, and also eventually they are presenting the final presentations. This is as a result, and then what we did like 2020 we started like a new English based program at SIT. This is the another short-term engineering English program departmental visit, which is like our Japanese students going to the India for the shorter like 2 weeks based program. So here like no at SIT, like a lot winter and summer breaks, more than like 30 to 40 students, batches of students to like going to the India. Like we started like 2013. Still we are continuing this program, IIT Madras and Anna University. So this was we systematically to dispatch our students. We made it like I made it my like departmental visits like English engineering program means that every day they have to learn 3 hours. Then cultural visits and cultural exchange, cultural trips. Normally, like we will be Saturday and Sunday the industrial visits. This program also like more successful. Our Japanese students are more enjoying to learning the Indian culture and Indian thing. This is the another one global full time. As a result of what I'm telling, like we made it like IGP, Innovative Global Program. This is the 100% English based program at SIT. And also graduation course also we started like 100% English based course, the master program. Students can be joined various departments. Of course, doctoral program is the fully funded. It's the 3 years program. Everybody is interested. Also, it's like more attractive. Here, like you can see the summary of the all our activities. World university ranking. Like this is the summary of the SIT efforts to improve the SIT ranking. So the strategic efforts were the 4 years, like 2013 to 2016. Then SIT successfully entered the Times Higher Education ranking. Then again, like Japanese university ranking, they started 2017. Systematically, we improved like 58 to 68, something like this. But however, like QS ranking is a little bit tricky because now the slide you can clearly contribute the enhancement of SAT ranking, but the this ranking, after like 8 years or 9 years, our participation we entered, because here like normally not only research quantity and quality, they are going to be like reputation survey. As a resultant, we took like a lot of efforts to make it here. Of course, as a resultant, eventually we entered like after 12 years. US ranking, ACR Pacific ranking, like ACR ranking, other ranking, now it's like within 3 or 4 years we entered. So any ranking programs, my suggestion, it is the entering also. It's like very important. Also, keeping this ranks also another important strategy. So, however, like even though Japanese university, then we can become the global university. Then now we are entered the all world ranking programs. So I will be move to the second part, research highlights toward the net zero energy future, integrating the superconducting technology with semiconductors. So here, like, before going to start my presentation, maybe like maybe some of the guys you don't know, in 1911, this superconductivity is not new. In 1911, superconductivity was first discovered in mercury by Dutch physicist K.H. Wonas at the Leiden University. When he cooled the temperature of liquid helium, like 4 Kelvin, like is the mercury, they suddenly occurred the 4.2 Kelvin, like 4.2 Kelvin, they suddenly applied the zero resistance. It's H.K. Boone awarded like 1913 Nobel Prize for the discovery of this superconductivity. So this is the science of superconductivity. In order to electrical wire made aluminum or copper, you guys know, so electrical resistance causes the energy losses. Then you can see like starting point and destination. It's always reduced like 5 to 7%. In contrast, superconductors have the zero electrical resistance. So electricity can be reached distance with the 100%, what I shown in the bottom of the picture. They called like Cooper pairs. The electron can be formed to the racing cars and travel to the lattice. That is the lattice vibrations. That's why superconductor means electricity flow very smoothly. Here, like a very interesting phenomena, we have to know about this. When the material transferred from the normal state to the superconducting state, expel the magnetic field from the interior. This phenomena, known as the Messner effect, it was discovered like 1932. This first observed 1933, Messner in the tin and lead materials. So this is called like a type 1 material, which are like HC, the critical magnetic field. Below is the normal conductor. If it is like a superconducting state, it become to the perfect diamagnet. Magnetic flux can be expelled. It will be act as a like levitate the any magnet if you are keeping. Then Onus thought one can be make it like very powerful magnets, because electromagnet means we have to send the current automatically, the resistance is 0. Then he thought we can make it. But here the logic of the type 2 superconductors, the critical magnetic field. For example, if you apply like a small, you can see like aluminum, cadmium, several TC superconducting Christian temperatures. But if you apply the external magnetic field, very small, 105 Gauss, the superconductor is going to destroy. Similarly, like several materials, lead and 100 Gauss, the very small magnetic field, it will be going to be disappear. Typically, almost all type 1 superconductors, around 1000 Gauss, superconductor will be destroyed. So this is like one of the great barrier. The dream of the Horus makes a strong superconducting magnet was only dream till 1960s. In the 1960s, the breakthrough comes, a new type of superconductor was discovered, that is called type 2 superconductors. That is like niobium tin. Here, the very important is like type 2 superconductor having the two critical magnetic field, that is called SC1 and SC2. Below SC2, it is become to the normal conductor. Below SC1, it is the perfect diamagnet. There, SC1, SC2 have the mixed state. We call like here like a superconductivity and a magnetic field is the coexist. In this case, like a magnetic means superconducting magnetic flux can enter inside. Then if you have a strong pinning centers, it will be trapped inside. As a resultant, one can be make very, very powerful magnets. That's why NBTI magnets now we are using the hospitals like MRI machines. Okay. Then you can see the example. This is the upper critical field. What we see like 100 oysterstars. Here, let's see entirely different. The what we are told like the NB niobium tin NB3SN. Now we are using like MRI emissions in the hospital. That is like SCT is 25 to 30, means high magnetic field application. One can be make like large 5 Tesla, 10 Tesla magnets. But recently discovered, like more recently discovered, yttrium-123 superconductor. That is what I told, like a high tissue superconductor can withstand magnetic field greater than 100 Tesla. That's why you can see like a YbCO, yttrium, barium, copper oxide. If you make it to a Y1, Ba2, Cu3OY, this can be, we can get the high TC, then more than 100 Tesla. It's very, very powerful. Okay. In that case, what is the key difference between the superconductors and semiconductors? Just I will give like, for example, like superconductors, zero resistance below the critical temperature, what we seen before. But the semiconductors, finite resistance, controllable, temperature difference, conducting only very low temperatures, but operating at room temperatures. Here the Cooper pairs is the main charge carriers. Of course, semiconductors is the electrons or holes. Like that's why we are making the p-type or n-type semiconductors. Here is the superconducting gap is the electron pairing, Cooper pairs. Here is the band gap between the valence band and the conducting band. Magnetic behavior, expel the magnetic field, weakly affect the magnetic field. Applications we can see like superconducting MRI, maglev trains, quantum computing. In the case of semiconductor transistors and diodes. So how ITC super can help the semiconductors? I think like in the future, carry electricity with almost no energy losses in the superconductor. No, this factor reduce the heat, a major problem in the modern chips. Enable the ultra-fast electronic switching, supporting energy efficiency and computing systems. Means less heat, less power equal to faster and greener the electronics. Why this technology is the matter for the future? Means help the overcome limitation of traditional silicon chips, enabling the quantum computers and advanced sensor, improving the data centers and AI energy efficiency. Further, we can think like supporting the clean energy and low carbon technologies. So superconductor help build faster and cleaner and smarter technologies. So here, why we did the clean energy. So it is help the fight climate change. Of course, reduce the fossil fuels, decreasing the relation with the imports, and promote the better public health. But here we can see like what is the current status of fossil fuels, because now still we are using fossil fuel means coal, gas, and oil resources is like limited. We can expect reservoirs are expected to be running out within the 40 to 50 years. It is the one of the major issue, of course. So that's why we are going to be like natural, like renewable energy sources, solar, wind, biomass, etc. But however, another problem is like since this industrial revolution, we are thinking now the global warming, like human activities have increased the greenhouse gases like CO2, CH4, N2O, O3. It present the atmosphere that decrease the just every increasing the temperature like earth, surface, ocean, and atmosphere as a resultant. Human induced warming reached more than 1 degree above the 2017. Now the people are thinking at present rate if it goes 1.5 degrees in the 2040. But biggest issues now last 2 years in the science and nature are clearly reporting that extreme heat and loss of Antarctic seas ice is the one of the biggest issue everybody is thinking, especially like recent surveys clearly indicate that climate change is the major global issue. According to the 2021 survey, around 60% of young people aged 16 to 25 reported being concerned about the climate change. They clearly indicated it affect their daily lives, including their work and sleep. So that it's we have to be properly work on how one can we do it. But here no, before I told that 2040 is the around going to reach like 1.5 degrees centigrade of the atmosphere temperature. But the recent data clearly indicates like on the Earth Day 2025 figures like 429.6 ppm. But even though to reverse the climate change, even partly, we will need to remove the order of 2000 gigawatts of CO2 from the atmosphere over the next century is the biggest challenging issue now. Then recently reported, like even though what we are talking estimated 1.5 degrees centigrade, they are going to increase not 2040. Is there we're putting like 20 before 2030 or something. This is the like imagine is really like more problematic. So how to control this situation? So it's like existing energy technology won't enough to solve this thing. New technology that reduce the environmental footprint is the very important, such as turn the renewable energy sources and also fuel cells. Apart from that, what we are talking like 2000 of megawatts of CO2, we have to be removed. Means in that case, we need like technologies to develop like carbon capture. That is also another very important aspects to how to work. So to win the war on the climate change, we need the technologies too. not only new technologies too. So in this case, I think question comes, can we reduce the pollution from the superconductor technology? I think it can be possible, but in that case, we need the low-cost routes of the optimum processing conditions. We have to produce like several type of superconductors, like low cost. We can say like LRE123 or MGB2 or bismuth 223, where HDSC cables is the one of the crucial. So ITC superconducting technology will be address the impact of the climate change. So you can see like energy transportation will be done by the HDSC cables, where like bismuth 223, RE123, MGB2 already well developed. On the other hand, energy storage, superconducting magnetic energy storage system, flywheel energy storage, which can be done by the bulk RE123 and MGB2 supermagnets. So here, just I want to mention why ITC superconductor, they first discovered in 1987, IIT6, Muller, Bednarz and Miller was discovered the new material, that is the lanthanum, barium, copper oxide, making the materials the higher temperatures. Within 1 year, 1987, Paul Chu, yttrium was replaced by the yttrium. Then raising the temperature base become the superconductivity to the around 93 Kelvin, the higher than the point of where the liquid nitrogen boils. This is the one of the very, very interesting, and people are started to work on this material to use the real application. However, this YBCO, when you are working, when you apply the magnetic field like around 4 Tesla, 3 Tesla, it is going to be 0, so that we cannot apply, we cannot use it the high field applications. Then what I did, just yttrium, what lanthanum to yttrium, then yttrium was replaced by the several rare earth materials, like more than hundreds of materials being worked on. Then what we found, one of the material, neodymium, europium, gadolinium, it will be like more than 15 Tesla at 77 Kelvin. This is like also showed the levitation at 90.2 Kelvin. This will be clearly indicate that one can be making like very powerful magnets, which can be useful for the fusion, transportation, as well as better medical applications. So this is the superconductivity, like superconductivity means at 77.3 Kelvin, that is minus 96, 196, but it is like very cheap, and from the air we can be produce the liquid helium. This is less than the mineral water. The current can be, once you generated, like we can say the persistent currents, like thousands of years, it will be current can be flow as long as the temperature is, you have to maintain the superconducting state. So here these materials can be, of course, one can be make it like using like processing the melt growth technique. What we develop like we can modified melt growth and melt growth. What I shown this the figure is the right side bottom, the processing condition, the modified melt growth technique. Of course, we have to. Here, very important is LRE Ba2C3 is the 1:2:3. So you have to maintain just mixing the powders and pressing it and sintered and slow cooling below the 1000 degrees centigrade. It's like very, very slow, 1 degree centigrade per hour, like 100 hours. Then eventually we have to oxygenate like 400 to 450 degrees, 600 hours. Means that depends how long. Even the samples are like larger size, we have to go like larger, like several days. Otherwise, it will be like 200 hours is enough to make the superconductor. So then we successfully produce the high quality bulk superconducting magnets in the world. First, this like this magnet can be like a trap more than 4 Tesla, 4 Tesla magnet at 77 Kelvin. I will show some of the data in the later. Here, one thing very important, like this the ternary energy 123 material. When we made like a magnet, the critical current density means you can see like a bottom figure, like x-axis is the magnetic field, 4 Tesla or 3 Tesla, almost all 0 in the YBCO system. But in the case of what we made, the energy is like very high, around 7 Tesla, which will be like we created the nano pinning using the inside like a GD211 smaller nanoparticles with the non-superconducting, which will be pin in the high magnetic field. As a result, and one can be make it like a very high critical current density. This showcase the several times like Superconductor Science Center the top cover for the this result. Then of course this amazing accomplishment were highlighted in many newspapers and TVs. They were patented in the US, Europe, as well as Japan, and the numerous awards in the worldwide, as well as Japan. This result. Then the second thing, we also made it like SEG and EG, where the new nanoscale pinning centers in the C like TEM. We made it like very small size, like few nanometers, like 30 to 40 nanometers, zirconia based nano pinning centers. It has been discovered, and also we had a new patent about I put it in the top of this. This breakthrough, no? This as a resultant critical current density, JC, I showed like 90 Kelvin. At the bottom picture is the 40 kiloamps per centimeter square. It is quite enough to levitate the magnet. But in the case of YBCO, it's the 77 Kelvin, what we showed. But here the 90 Kelvin, the first report. This is the fundamental, and also this is one can be used. This non-contact liquid oxygen forms from the hospitals, and also rocket launching technology for the superconducting berries. Again, these results also appeared in the news and TV, responded the patent. It's also like won the awards from the Japan and different countries. So anyhow, when you want to use something like at 77 Kelvin, for example, just some like a black diagram I'm showing here, 0 to 14 Tesla, then JC. You want to make the application, the motor is the 1 to 3 Tesla is the very useful. Of course, like some of the applications, the maglev or flywheels or MRI machines, it will be like around 2 to 5 Tesla. But people are working now fusion magnets. That case, like they need the 14 Tesla, 10 Tesla, 15 Tesla is very, very important. But in this case, there is no new now at that time no material. But even though it's like at 77 Kelvin up to date, this is the one of the champion data. What we did like here, the new class of nanoscale pinning media ranging to very, very like nano order. This is the coherence length close to coherence. When we are manipulating the matrix ratio 1:1.25, 0.085 means it will be a rich direction. We made it like nano pinning inside like 3 to 5 nanometers, what I shown the STM. As a resultant JC, you can see what I shown before, 4 Tesla to 7 Tesla, but here the exactly double, that 40 Tesla. Means when you control the microstructure in this the 1, 2, 3 matrix, one can be more like very, very high irreversibility field, which is the one of the very, very important. Like there is the high field applications using the RE123 materials, is introducing the flask pinning centers is like nano order is the very, very important. We already know we did like this experiment like several like TEM, DFM, STM scanning, tunneling microscopy, all this. Then we estimated this nanoscale, what is the composition, everything. Eventually we found like LRE rich clusters is forming to the nano order. So as a resultant, such a material, just we made it like several large, because no, this trapped field is the proportional to JC into R, means carrying capacity into the diameter of the material. We made it like a world highest large size material. As a resultant, you can see the bottom. One can be make it like 17 Tesla, 17.6 Tesla at 76 Kelvin, or in any case, even though 90 Kelvin means very, very high temperature, close to the supercontraction temperature, one can be make it 5.5 Tesla. But however, the permanent magnets, we cannot go like 1 Tesla is the very maximum. We can have more than that one. It is very impossible. But in the superconductors, no, there is no resistance. One can be make it very, very strong magnets. Okay. But the other challenging, when we are working this, is like 2 centimeter or 4 centimeters superconducting magnet is like $3,000 or 4,000 to reduce the price. No one is listening. Then we made it so systematically, like I explained, like batch production. In our case, like, of course, we optimized so many things, and also we used this again, the new patent. Then we made it like more than 60% of reduction. Now, eventually, this batch production now is like more successful development of RE123 systems, like low cost and making the world planning reports. Then people like so many companies are producing like yttrium 123, gadolinium 123, yttrium 123, ideal material for the permanent magnets. That's why they are making the so many like batch production. Then I will show some of the applications, medical and healthcare. This the superconducting supermagnets will contribute the good health and well-being. Here the important, like medical application, novel medical treatment without surgery. You can see the left hand side is the superconducting magnet, right hand side is the permanent magnet. So when you use like a superconducting material, like the strong and steep field of gradient generated by the HDAC material will be control the drug in the desired part utilizing the Fe particle. But in the case of like right side permanent magnets, like magnetic field is always flat, even though you can see the permanent magnet or solenoid magnet. And also it will be, we cannot generate the high magnetic field, so that you cannot control the drug. This is the one of the example. We made it like a strong and steep gradient generated the STSC material will be control the drug inside the your body. Normally, the magnetic field is placed the outside of the body. The magnetic seed drug is injected into the body vessel and navigate to the desired part by the external very strong magnetic fields. So this can be applied, like even though this is the one of the this is the like drug stray system for the knee. Like normally nowadays, like old age people, they always get the knee problem. That in that case also seam cells with the magnetic particles. If you put it and externally control the magnetic field, normally this is the ideas we made it. But in the always in this case, we need the bulk superconducting magnets that will generate the high magnetic field, 5 Tesla. The size is 2 centimeters. Just our students are still working like making the more performance of this material. Of course, recent days, no, this medical, this like strong and several commercial products now available on the market, including the HDSC bulk levitation mixtures, which is also very, very useful for the medical field. So this is another example, like one can be using like water cleaning. Due to the strong magnetic field of water purification employed the high tissue superconducting magnets, like in the laboratory, what I am showing the right side, that is one can be make it like over 90% removal of the algae or fungi or something particles, ferromagnetic particles, like even though industrial waste, we can be clean it. This already like Kyushu Electrical Power Company was made it like a mobile type water cleaning system. I had made it like in the Kyushu area, several lakes and ponds. This is the one of the commercial products. So this due to the like strong this thing, one can be make it more thin. So then one of what is the transport application one can be use it this material. Transport means always okay, they need like real reliability. Means of course this is like low carbon vision strategy is the one of the big player. Even though Prime Minister also in Japan declared like they want to make like the 50% of CO2 emission is 2030, 75% is 2050. Then everybody is putting efforts more in the railways also same thing. Like if you look this thing always top left figure clearly indicate like highest, lowest, almost all CO2 discharge is the maglev, magnetically levitated train, or maglev evacuated tapes. But of course, this, and also we have to consider the speed. In this case, like bottom picture, the maglev trains is like more than like 600 kilometers per hour. Then this research was started in 1972 at RTRI, achieved the speed like 60 kilometers per hour. That's like maglev ML 100, the left hand side figure. But recently, This like Central Railways has announced that the real superconducting maglev is like Tokyo and Nagoya. It's the around like 380 kilometers, like 40 minutes using the superconducting magnets. But they started like 1972. There is no high TC material. They made it like low TC niobium tin magnets to utilize here. Then what I showed, not only like niobium tin, then I made it like a prototype homemade maglev vehicle. Then I showed like you can see like very easy like very small like 3 superconducting magnets. There's a field cooling in the left hand side figure. Then like kids are enjoying using this maglev model. Then eventually that like this was successfully created high TC maglev. After this result, prototype vehicles like utilizing the high temperature superconductor showed various countries like China, Russia, as well as Germany, and also like a prototype vehicle like a maglev Cobra developed the Brazil, utilizing the same yttrium-123 superconductors and levitation for the transport system. This is like the world first high temperature high speed maglev, like large type of prototype was designed by and reported in January 13, 2021 in JU from the Chengtong University in China. So again, here is the prototype HDSC maglev evacuated tubes. Also, of course, everybody knows the Hyperloop. Now the in US and Germany collaboration they are working, but this is the research collaboration with SWJ. We supplied the YBCO material and we made it like 150 kilometers per hour inside, and now we are working at 300 kilometers per hour. All these things, no, one can be reduce the low carbon emission and increase the our lives more easy. Then again, another type of material what we are using the production of low cost and high performance bulk MgB2 material that is called magnesium borate. This is like MgB2, no? It's one of the most low cost, high performance, lightweight. One can be used in several industrial applications. Of recent days, rare earth is the problem. What I showed is the before is the rare earth based material like neodymium, samarium, europium, gadolinium. That will be make it like 1:2:3 ratio. It will become to the super magnet. But here there is no something like that. Is the Mg magnesium and boron. Here is the very interesting. One can be make it like a power transmission, magnetic resonance image, MRI. Now Hitachi and ourselves we are working together to MRI machines using the MGB2, like of course electronic devices, everything. End user, energy sector, medical sector, aerospace, industrial manufacturing, several things. One can be make the superconducting tapes, and we can use it the low temperature. Here, the one of the major issue is you want to increase this performance, means we have to increase the critical current density. What I shown in the table, motors are generator, we need the 100 kiloamps per centimeter square. Transformers, 80 kiloamps, then current limiters. Where this the Mg and boron. Boron is the one of the major drawback. Like boron melting temperature is 2500, 2200. Magnesium is 600. Magnesium melt and react to the boron from the MgB2. So boron size is the smaller and smaller. It will be act as the grain boundary pinning. As a result, the performance goes up. Then people are trying to use like nano order boron, but no one was succeeded. But we did it like ultrasonification, new technique. This is like one of the cheapest and lowest, and we cannot make it like large quantity nano boron using this technique. You can see the commercial boron to nano boron. This like we did like a propanol 45 minutes. This the XRD is the top. There is no contamination at all. But if you do the ball milling, of course we can make it the smaller size, but the large contamination, what I shown in the bottom, they are reported in the literature. There is a PhD issue. Then here, like our students and myself, we designed this equipment the more properly to industrial low cost and optimal processing conditions for the using the ultrasonification technique. Then this slide shows the boron utilizer 2 propanol like like this right hand figure, you can see like you can control when you are making like high energy ultrasonification, generate the very powerful like heat waves and pressure. As a result, and it always heat up this slurry, so that we put the especially we designed the cooling system and everything. When your nanoboron is ready, just like mixing and sintering and making the superconductor very easily. This is like a production of the nanoboron. This is the when you using like the gravitational effect, high energy ultrasonification create the ultrasonic wave, liquid and forming and collapse the bubbles called the cavitation. During this process, like no, it will be generate the high temperatures and pressure, shock waves and jets. When it is created, the jets and high powerful waves, it will be like when the boron particle comes around there, it will automatically break it. And this process is be continuously running. One can make it like a nanoboron. This is the one of the more very pure. One can be make it like a very high, smaller size up to date. Then during this process, what we found when you utilize like high viscosity ultrasonification media directly pop the bombarding effect, like a drag force is proportional to bombarding impact. As a resultant, the particle size is going down and JC is going to increase when the viscosity is going to be increased. Then as a resultant, like just we use like a high heptanol. One heptanol is the this high viscosity material. So notably particle size was go down to the 170 nanometers. This is up to date, no one was reported. Then the XRD results, you can see the right hand side figure, XRD like several hours ultrasonicated in the heptanol, 0 minutes to 135 is still like there is no like contamination. Normally B2O3 peaks is the one of the major issue here. We are not seeing anything like we can see like it was free of impurity phases. Such a boron powders one can be utilized in the UKIT. This is like simple processing like when your nanoboron is ready, then the thing is like we have to mix the magnesium and boron in the glow box. Otherwise, the magnesium is if air we cannot do is it will be like react with the oxygen in the air, it form the MgO, that is the non-superconducting particle. That's why normally people can do like mixing in the glow box, pressing, sintering just like 3 hours. It will be get the superconductor. It's very easy, low cost, lightweight. So recently again, when you use like this particle, this is the eventually like made it like a final microstructure of the for samples. One can be like main particle size when you are going to 120 minutes nano. After all particles we added to the MgB2 for production, we observed like 153 nanometers. Then this is the result. We also comparison of the commercial boron and nanoboron plus nanoboron with the carbon dopants. As a resultant, what we found like optimum dopant sample we show like with the one of the JC is the 492 kiloamps per 20 Kelvin and 720 kiloamps per 10 Kelvin. But we are expecting like 100 kiloamps per centimeter square. Our students are still working to reduce the particle size nanoboron. Of course, this is we went around like 150, but we can go like coherence length of the MGBT around 12 nanometers. If you go like even still we have a large room, we can go like 150 to 72 nanometers, 17, 12 nanometers. But in that case, we have to be optimize the so many things. Of course, further you can use like high viscosity material and time and frequency and temperature, so many factors. I hope we will be reduce the particle size further to improve the performance of this MGB2 material. But here the interesting, like we are working the Hitachi, like we need like 5 Tesla MgB2 bulk magnet for the MRI, magnetic resonance image for the hospitals. If you make it like a MRI machine using like MgB2, it's like a very low cost. There is no doubt. That's like a price will be goes down the hospital charges. So here we process like magnesium powder and the commercial boron is the expensive. That's why ultrasonification boron. If you made it 5 Tesla magnet. That's like you can see like 1 Tesla, 3 Tesla, 5 Tesla. If you increase in the magnetic field, this MRI pictures will be very, very clear. So production of the nanoboron is the one of the greatest idea to increase the MGB2 performance to make this thing. Then recently what we did, like we made it like MGB2 cryomagnet using the SPS, spark plasma sintering, not solid state sintering. Whereas very simple, like during the processing, just we have to be apply the high pressure and high temperatures. As a resultant, you can see like a size of 20 mm diameter, 6 mm thick, very, very small, like 10 mm coin. Then the trapped field is the bottom. This is the like 4 samples, different combinations. We changed the like magnesium rich and silver rich and carbon coated boron, something like that. Then eventually like MGB2-1, you can see like 15 Kelvin more than 4.2 Tesla. Very small piece of sample, like 20 mm by 6 mm. It will be 4 Tesla. When we, because now it is very small, just as the same samples, MGB2, 1, 2, 2, 3, just like we sandwich, and we measured, this is like a 10 Tesla, like 15 Tesla, like this is like a sandwich sample shows the very, very high trapped field. Up to date, no one was reported. 15 Kelvin, like 5 Tesla. Then what we found, we controlled to the nanostructural pinning inside the material. And also we found like a new class of nano pinning centers, that is like a MGB2 O particles. You can see the elemental analysis in the top table, like magnesium, boron, and oxygen. It will be clearly indicate like no, it will be make it like nanoparticles, like around like a few nanometers, like the maps right side, like TEM maps clearly indicate that, like I put it like A1, A2, A3, A4, A5, all these are oxygen content. The oxygen map reveal the distribution of the higher oxygen content in the MGB2 nanoparticles. The ETX clearly indicates this is the new type of new class of nanoparticles is goes to the coherence length. That's why we found like a 4 Tesla magnet. So here is the some comparison. You can see like now we are using the 1.5 Tesla MRI emission. This is the 3 Tesla MRI emission and 5 Tesla MRI emission. But recently, what we found, like 20 mm by 5 mm, we can get it like 4.21 Tesla. Just like sandwiched sample, 6 Tesla. Very, very small size. If you use this material to make it the coil, we can make the very high powerful superconducting supermagnets. This we also made the patent of this material. So I think like in the future, ultralight superconducting magnets, if you use it like low cost, because it's the magnesium and boron is the comparatively rare earth, no, it's a very low cost. One will be make it. These things further reduction of the price, one can be used even though like windmills, automobiles, rotary applications, washing machines, whatever it may be. This the one of the work what we are pursuing. Our students are making like further improvement of this material for the real world applications. And another is the like power transmission and generation. Now the superconducting power cables is the one of the key players. Like we have like several type of materials. Yttrium, barium, copper oxide cables, and bismuth 223 and bismuth 2212. So like MGB2 cables and others, etc. These cables now the worldwide, so many companies are working like US, Europe, Japan, and Korea, and China. They are making like kilometers of wire and making like this thing. Of course, this is like the one of the major thing. Global superconducting cable projects now the increasing the day by day. Like people are expecting 700 million by the end of 2027. So something like I think in the future it will be more demand due to the energy transport, like when the electricity transmit from the power station to home, so already shown like 5% is lost. which is roughly the same of the output of the 6 huge power plants in Japan. This is a simple example. So I invested the more to make the new class of RE123 superconducting wires, like first made the silver sheeted tapes, then also we made it the first, this the initial composition, the 2-1 and liquid phase one could make the 1-2-3. Then superconducting wires are made it. This is the first report, and it is like 150 amps at 77 Kelvin. It is sufficient to use the real application. This is the first report on development of new class of RE123 PIT developed RE123 tapes. So these superconducting cables are like more attractive for the future application because the bulk power transmission and also like local distribution where the space is limited, one can be used like a compact and very powerful these things. The German and US based companies, even though German and Russia based like Airbus, they are using the future electronic aircrafts using the superconducting cables. Then I will show you here the one of the railway application. Here the benefit of what is like load leveling, energy saving, CO2 emission reduction. This is the main idea we came like this thing. Then JST people are asking how, what, where we can use this DC cable. But you can see like DC electrification is like more than like 71.6% private lines and 36% the conventional lines they are using, so that it's more useful. Then here like a major what is HDAC cables is the red one, DC cables is the black one. If you use the superconducting cables, like due to like substation spacing normally 2 to 3 kilometers along the rail track. If you use the superconducting cables, then we don't need to use the substations. Otherwise, 30 kilometers one rail route, we have to put the certain substation due to the DC, it will be decay. But almost all the Tokyo area and Osaka area, all the railways, like subways, is run by these DC cables. So that they were designed, we included the of course, government is more keen about the CO2 emission, so that this project was more successfully be handled. Then, if you use it like a normal conductor, just we have to here they change the superconducting cable using the substations, so that if there is no substation, we can reduce the 5% of the electrical loss and also substation maintenance. Everything will be and further the CO2 emission reduction. This is like a prototype 2-meter cable. We designed, we systematically, we analyzed the Bismarck 223. But in the case of railways, they need the 1.5 kV. Then we measured using like a local made cryostat in the top figure. Then you can see the bottom, the result 1.5 kV is the very clearly indicate like even though 77.6 kV, the black one, you can see like 1500 kV, the resistance is 000, this is moving upwards. If you go the lower temperatures, we can get it like a more high field current. Then subsequently the question comes, so one can be used it, this material, we are sending 1.5 kV, what is would the liquid magnetic field? Because is the almost all like in Japan, major challenge in liquid magnetic field. The Tokyo area train tracks are located very close to the residential zones. So designing the system with the current flow. But what we did, like we designed this cable. We are sending like conducting layer and also like both layers, currenting layer, opposite direction. The influence of the liquid magnetic field are tested. And then finally we found you can see the both conducting layer and shielding layer. When you send the current in the opposite direction, almost all zero. Means one can be make it like there is no liquid magnetic field effect. One can be use it railways very easily. Then the major project was started. Then we made it like a 5-meter long Bismarck 223 cable. This is the right side is the result and left side is the cryostat testing the 5-meter cable. So we found the very high 1.5 kV is the almost all like different temperatures like 70 to 66 Kelvin is this like very clearly indicates one can be used this cable is for the real application. Then we designed the construct the prototype like 30 meters and 300 meters Bismarck 223 DC cable and succeeded the trend run test. You can see the bottom. The cable is the same similar to the normal cable. Here the future like 2050 vision is the next generation railways. They want like they want to use like solar energy. So DC it will be connected directly to the train system. And also in the future, they have like HTC power stations. They will be stored the current in the nights. They can be use it for the run the trains. Here is like this is the Miyazaki test area. Planned the development of 3 to 4 kilometers of DC cable project, utilizing the solar panels for the DC power. So it's like now the efforts is going towards the like Miyazaki test center is the DC cable project utilizing the solar panels. So what I want to say that let's always know this like solar as well as like superconductor cable. If you connect, it will be works very well like future energy needs as well as CO2 emission reduction. So here just I am putting our slide. In the upcoming years, DC superconducting cables are utilized to effectively transmit the renewable energy, particularly solar power from the 365 days sunny regions to colder countries. Of course, I told like very beginning, for the 40 to 50 years, the fossil fuel going to be run out. In that case, we have to depend on the solar, where maybe in India is the one of the potential candidate. Like if you produce the electricity using like a solar park, like a desert, already Indian government is started like 140,000 acres in the Rajasthan. If you produce the electricity, even though if you want to transfer from the India also, they need like very special cable. If you use like a normal the DC to AC, then AC transport from place to another place, a lot of losses. But if you use directly DC superconducting cable, of course, North India to South India, we can transport. If you have a large energy generation, one can be make it like even though Europe or Asia, because so many countries are the golden countries, they cannot put it like 365 days sunny regions. So this is the another very important. This the superconducting cables is the very crucial in the future. So superconductors plus semiconductors enable high efficient clean energy systems. Of course, semiconductors controls allow loss-free power transmission using the superconducting DC cables. Together, they reduce the cost, support commercialization, and accelerate the path to the net zero energy future. So like that, I think superconductors plus semiconductors. I think if you think something like this, I think one can be make it like we can be reduce the pollution, means greenhouse gases. One can be increase the more viable like power consumption to the public. Thank you very much.
Thank you, Professor Muralidhar. Uh, yeah, any questions from the participants can be written in the chat.
Thank you very much, sir, for such an inspiring and intellectually enriching session. Your insights into advanced materials and sustainability were truly enlightening.
The manner in which you connected fundamental research and real-world semiconductor applications has set a strong foundation for this FDP. We sincerely appreciate your valuable time and guidance. We have time to take a few
So,
questions. So if anybody
yes,
has
and
any
participants are
questions,
requested to.
If there are any questions, please write in chat box. Our coordinators will take it forward. You, Shivam and Karishka, you can check if there are any questions in the chat box.
Sure, ma'am.
So I am
Yes, ma'am.
looking, I have not found anything.
Okay, okay. Uh, to the participants, if there are any questions, you can write an email to us, which we can forward to Professor Muralidhar. Sir, it was a wonderful session, and we would like to see you in the North Cap University, as it was discussed with Professor Sharda. Whenever you are visiting the North Cap, India, do visit the North Cap University. We would like to host you and learn many things from you.
Thank you so much for your kind invitation. I will surely join
I
in the
am Dr.
future.
Pooja. I work with Professor Sharda as a Deputy Dean International Affairs. So
I
we
see.
work closely in the international office. Yeah. So I would love to host you, sir, at the North Cap University. Whenever you are in India, please let us know.
Sure, sure. Thank you so much.
Yeah, thank you so much, sir. Thank you so much taking our request and giving this session in a very short notice even. Thank you so much.
Just I found one question just a minute. Very interesting results. Just one question. Why
Yeah.
superconductor superpower USA not able to develop the levitation trains? Any particular reason? I think, of course, this the first patent and proposed in the US only. But even though they developed the lot like no air-based systems, it is like of course it is a little bit expensive and also work very hard. Like before superconducting supermagnets designed by the low TC magnets, that is the niobium tin, it's supposed to work 4.2 Kelvin, little bit expensive. But after discovery of ITC superconductivity, that is 1986, more than 25 years, they made it like development of superconducting wires. Now, the several companies like in Japan, Fujikura and Furukawa, Sumitomo Industries, they are making like kilometers wires as well as superconducting cables. I think this is the time. I think even the US also thinks in the future when the superconducting train run by the Japanese government in the 2030 from the Tokyo and Nagoya. There is no doubt they will be also try to do. At the moment, lack of low cost material like ITC material. Yes, right. Superconductors and semiconductors, two different kind of materials. What I showed, there is no doubt. But however, no, how the semiconductors like what like we are working like perovskite solar cells, highest efficiency they are producing the solar energy. But when the DC superconducting cables are one can be use it like to transmit the current from one place to another place without any losses. So that if you combine the solar panels to the DC superconducting cables, maybe the one of the great advantage. So that we have to connect the superconductors and semiconductors, even though do different fields, it doesn't matter. Now the people are working like supercomputers using the qubits technology, that is like superconducting thin films. I think next to superconducting now in the US and also Japan and Europe, the people are working the supercomputers. No, they're all like superconducting technology only. Of course, the different material prospects, I can agree. But if you join, if you connect the semiconductors and superconductors, the very great advantages. What are the advantage of superconductor atomic energy? Yeah, that's a good question. But normally, no, like people are working the fission magnets. They need like the fission reactors. Normally, they developed the very high powerful like plasma. This plasma can be controlled only superconducting high field magnets. That is need like 15 Tesla or 20 Tesla magnets. Now recently the people are working like Europe, like Asia, and also like I thought today I'm discussing the Indian embassy in Tokyo. In India also they are trying to work on like superconducting. This is the fission magnets. what this one? At 20 Kelvin, the thermal conductivity of the MGBT is quite different when the 4.2 Kelvin. Does the entropy margin of the MGBT at these temperatures make the train more reliant to the sudden quenches, losing superconductivity compared to the traditional NVTI magnets? Oh, still like people are not thinking to the MGB2 magnets for the this maglev system. They are using the YBCO or like LRE123 based material because NBTI is the 4.2 Kelvin, MGB2 is the 20 Kelvin, not much difference. But if you use it like YBCO based like RE123 based material, we can say the 123 materials, that is like an 77 Kelvin. One can be make it like low cost super magnets. So that is the more viable magnets for the MRI, this maglev systems. Now Japan, they are working like RE123 based super magnets for the railway system. What effect will be these magnets have on the LHC? What is LHC?
Mr. Sumit Singh, please mention what your question clearly in the chat box.
They are talking like AC losses. Heat generated by the changing the magnetic field can
Particle
be.
accelerator. Particle accelerator, he's mentioning.
Yeah, particle accelerator is the different story. They are using in.
Sir, on the website it is written Large Hadron Collider.
Right, right. Yeah, normally, like you want to see the like atomic like neutrons, protons there to control they see their activity to find out the new physics. Normally they use the high magnetic fields. That's why like superconducting magnets somewhat it will be useful to see their their new particle behavior of these protons or neutrons or atoms behavior using the high magnetic fields. That's why the people are trying to use like superconducting magnets in the particle accelerators.
I think no other questions are there, right? Any other questions? So there is one more question. Yeah, there is one more question in the chat box. In fact, two questions are there.
So do superconductor conduct electricity like normal transmission wires? Normal transmission wires means that the room temperature superconductors, not now. Now the materials can be superconductors at 91.3 Kelvin. For example, like YBCO case is 96 Kelvin in the neodymium barium copper oxide. Like bismuth 223 is the 120 Kelvin. Professor give the recent progress of RIPCO rare earth barium copper oxide tapes. Do you believe MGB2 bulks will be remain the superior choice of magnetic levitation due to their lower anisotropy and cost, or will these more hybrid system in the future? Of course, I that's why no, I am working like both systems like RE123 and also MGB2. After working long time and developing like so many techniques like melt structure shredding, OCM, oxygen controlled melt growth, IG process, and now it will be taking like long way. Like if you want to make one 3 centimeter superconducting YBCO super magnet, it will take like more than like 1 month. But in the case of MGB2, just 1 day, one can be make it like high powerful magnets. So that I think MGB2 is the lower temperature. It will be superconductor. We can application can be expected around 20 Kelvin, but the performance wise, cost wise, and their performance wise, MGB2 is the one of the best candidate from the specific applications. For example, like if you want to going to make like MGB2 bearings, normally like space applications, lightweight, no, one can be use it. S-
So there is one question. Why superpower USA not able to develop levitation trains? Any particular reason?
that indirectly I told now that like because in US not much interested because they developed the flights like so many like transportation done by the aeroplanes. Meanwhile, like low TC materials is the too expensive. But now recent days, high TC material like yttrium bearing copper oxide, neodymium bearing copper oxide, gadolinium bearing copper oxide is developed. Recent days, they are producing like superconducting wires for the kilometer. One can be make it now. I think in the future they can.
Right.
Because
What
in
about
the in Japan, like what I showed, like 1970s, they started like maglev system. They are using like low TC material. It is little bit expensive. And also like they cannot use it like old tracks or old systems. They have to make it like new ways. That's why like in Japan, like Tokyo to Nagoya, it will took like more than 4 years to land acquisition. Now almost all land acquisition is completed. Then the track system is almost all finishing. So that's why they are planning like 2030, like 380 kilometers, it like for around 38 minutes. It will be like the superconducting train. But apart from the magnets, like superconducting cables will be like crucial in the future. If definitely it will be useful for the India too, while we are working like solar or wind, whatever it may be, any renewable sources, it will be directly generate the DC. This DC without any loss, one can be transport from one place to another place means superconducting cables can be done.
Krishka, you can see if there are any other questions.
No, ma'am. I think sir addressed all the questions.
So no more questions from the participants.
I would just request the participants to fill out the feedback form in case anyone hasn't filled it out.
All are requested to fill the
Ma'am, there is
feedback form.
one more question in the chat, I think so.
Yeah, please read it out.
Sudden health for knee joint pain in India. Stem cells are injecting into the pain
Yeah,
area
yeah,
now.
yeah. I'm looking. Actually, no. Of course, I just like superconducting magnets. One can be use it to like several applications. Is like a medical new class of. Is asking like a giant pain something like any technology, anything they want to use it. Like no, first they have to be approved the medical society or something. It will be take some more time. Something like that because here in Japan, this is the same technology working the Tokyo Medical University to real issues. But our main exploitation is the developing the super magnets and putting some sketch how one can be use it, what is the importance. So I think in the future all this technology will be come out.
Right, sir. Thank you so much, sir, for taking the queries and giving such a wonderful session. Thank you so much, sir.
Thank you so much for inviting me and interacting me. Thank you very much.
And I would love to see you soon in person at the North Cap University very soon, so that we can
Soon
meet
and
in person
also
and discuss a lot about this topic.
yeah, sure, yeah.
Okay. Okay. Thank you so much, sir.
Thank you. So
So you
We
can
now
leave the
proceed.
wait, Krishka. Sir, if you wish, you can leave the session. It's as per your choice.
yeah, because already here is 11:30 p.m. So I may leave
Right,
because
right.
I have to go tomorrow morning again early hours. So
Yeah,
thank
sir.
you so much.
Thank you taking out time
Thank
at
you,
this
sir.
hour of yours.
Yeah, sure.
Thank you. Okay, okay. So Professor Ramachandra is here. Krishika,
Yes, ma'am.
they are here. So I think we can start with the next session. Professor
So,
Ramachandra,
ma'am.
can we start? Have you made him presenter and unmuted his mic and camera?
Ma'am, he's the
Please speak once
presenter, but his mic is muted.
and he's unable to unmute, no?
Mm,
No, actually, he's a presenter, so he has the rights to
He's having
unmute
the
and
right.
yes,
So you
yes,
can unmute. Um,
Yeah. Am I audible now?
yes, sir.
yes, sir.
Yeah.
Good
Shall I
evening,
share
sir.
the
Namaskar.
PPT? Good. Namaskar. Namaskar.
So nice to see you again, sir.
Yes. We will be seeing more frequently in future
Yes,
also.
yes. Very
Yeah.
right. So can we start, sir?
Sure.
Okay. So Krishka, you can first introduce her and then share the presentation slides.
sure, ma'am. We now proceed to welcome our second speaker for the day, Dr. C. Ramachandra, a highly respected expert in semiconductor fabrication, clean room technologies, and nano manufacturing.
Dr. Ramachandra brings with him over 40 years of experience across the semiconductor value chain, including wafer manufacturing, chip fabrication, testing, packaging, failure analysis, and reliability engineering.
Dr. Ramachandra is a recipient of the prestigious UNDP Fellowship, through which he gained extensive hands on experience in the USA and Europe on 3-micron CMOS technologies, laser beam systems, and advanced fabrication processes. He played a crucial role in establishing nanofabrication facilities in India.
His illustrious career includes contributions at ISRO, Siltronics India Limited, SIRI, Micron Wafer Fab Singapore, Dassault Semiconductor, and CMTI, and he was instrumental in introducing VLSI circuit edit technologies in India for the first time, providing cost-effective solutions to VLSI design industries. The chat box will remain open and the Q&A will be taken at the end of the session. And we now invite Dr. C. Ramachandra to kindly begin the technical session too.
Thank
Over
you
to you,
all.
sir.
Today I am going to discuss or present on processes, namely lithography and etching techniques and show you how important it is, how critical it is, how challenging it is in fabricating semiconductor devices. These techniques are not only limited or specific to the semiconductor device fabrication. They are quite useful for fabricating many nanostructures, nanosensors, smart sensors also. Therefore, it is important to understand the various challenges, various complications are associated with these techniques and technologies. So if you look into the semiconductor device fabrication, it has several processes. In fact, the whole fabrication cycle takes from 2 to 3 months. In this, the main key process are lithography, etching, and deposition. So I hope you people are seeing the PPT, any limit problem? Hello?
No, sir, we can
It's
see the
visible.
PPT.
It is
Yes, sir,
visible.
it's visible.
Okay, okay. Now, if you consider semiconductor wafer fabrication, the starting material, that is the input, is basically silicon wafer. Today, most of the 80% of the devices are made from silicon. However, there are certain special applications where the wafer is not silicon. It can be gallium arsenide, it can be gallium nitride, etc. But I'm talking about 80% of the applications. And output is certain functional devices, which is useful directly in the industries or in the applications. So you might have silicon wafer. Typically, it started with 2-inch, then grown to 4-inch, 6-inch, 8-inch. Today, industry is working with 12-inch wafer. So that is the increase and improvement in the diameter of the wafer. That itself is quite challenging. How to grow 12-inch crystal? Anyway, we are not discussing that one. But today, industry standard is 12-inch wafer. This is the starting. And after it undergoes 2 months or 3 months in the wafer fab, what we are going to get is output. That is a usable device which you are using in the lab, which you are using in many projects. This is the chips or this is the output what you are going to see. It will take 2 to 3 months to transform silicon into this kind of usable chips. So in this process, what are all the critical process? What are the challenges? What are the limitations? And what are the opportunities for R&D? That is what we are going to see. When we say electronic circuit, it has different types of application, different types of circuit configuration. It can be configured as an amplifier, oscillator, logic gates, adder, multiplier, encoder, decoder, filter, microprocessor. I have not listed all. These are all some familiar functional blocks what we are being using in the lab. In fact, if you go back to the history, the transistor was first discovered in Bell Laboratories in 1948 by 3 scientists, Bardeen, Brattain, and Shockley. They got the Nobel Prize for this one. This was in 1948. Now, if you look into the development, in 1947, the first transistor was developed, but it took 15 years. Remember, 15 years to integrate 4 transistors in a chip. That means in around 62, 63, we are successful in making integrated. That means solid state operational amplifier. So it took 15 years, but to integrate 4,000 transistor, it took less than 10 years from here to here. So the growth has become very, very fast. And today, you know that in a single IC, like microprocessor, we have more than 10 billion transistors. That is you can imagine how we have been growing from last 50 years or so. How this growth has come? The designer has challenged the industry. You give me enough number of transistors, then it is my headache to integrate. It is my headache to generate and deliver the circuit you want. You just give me more and more number of transistors. That is the challenge put by designer. and how to put more and more number, because chip size is not increasing. Therefore, the only way to put more number of transistor is miniaturization. That is the driving force for last 50 years or so. We have been reducing the transistor size. We are putting more and more number of transistors in the same chip area. And as a result, today, number of transistor, which is one of the important key metrics, has crossed 10 billion in a single chip. Of course, if you look into the semiconductor device, whether it is a microprocessor, whether it is an operational amplifier, whether it is a filter, what it contains, it has only 4 elements, nothing more than that one. One is resistor, one is capacitor, one is diode, one is transistor. You do not see any fifth element in this one. Any circuit, any device you take it, it is made up of only these 4 elements. Then what is the difference between simple circuit and complicated chips? Only number of diodes, number of transistor, number of resistor, and how many transistor, how many diodes are placed, how they are interconnected. That is the challenge. That is the one design people are accepting and generating more and more complex circuits. So any device is there, you will not see anything more than these elements. In fact, nowadays we have got some special device called MEMS, where some inductor is possible to integrate, but that is a special category. We don't consider in this general purpose. So how a transistor looks, for example, I said there are 10 billion transistors. How it looks? We have source, we have gate, we have drain. This is a MOSFET structure, which was very familiar for many decades. From that, we have moved to the FinFET structure recently, where gate and drain. Gate is a fin type of structures. Then recently we have moved gate all around. That means gate is floating and all around. So this is to improve the performance of the transistor and put more number of transistors. So wafer fabrication, as I said, actually, it is a batch process. It is not that single device is processed actually. In one wafer, typically we have 1,000 chips, typically. And like that, 25 wafer forms a one lot. So it is a lot process. And circuit integration, though we have billion transistors, it is integrated to do certain function. That is a challenge or job of the design people. Number of transistors, it has crossed 10 billion. So we are able to meet the challenge of the designer. What they said, give me enough number of transistors, we can realize any circuit function. So there is a now competition between designer and the manufacturer. So we have been successful in providing more than 10 billion transistors in a single chip. Now it is a designer how best to utilize these transistors and other components and provide different functions from the circuit. Now if you look into this one, how we are able to put 10 billion transistors in a single chip, whereas chip size has not increased much. We have gone through the technology node improvement. This is a 20 micron technology node. What does it mean? 20 micron means typically it indicates size of the gate. So if 20 micron is size of the gate, the transistor size almost you can take double. That means maybe 40 micron. So from that one, we have been reducing the transistor size or gate node 20 micron, 10 micron, 6 micron. Like that, actually, if you have heard, actually, we have realized 2 nanometer in 2025, and people are struggling to have 1 nanometer in 2027. That means same chip size is same. We are reducing the area of the transistor. As a result, we are able to put more and more number of transistors in the single chip. Then what is the challenge? Is it an easy job? Can it be done without any difficulty? No, that is what we are going to discuss. When we reduce the size, what are all the challenges comes, how difficult it is, how it has been implemented, how problems are solved. These are the things we are going to see in next couple of slides. Now, if you look into this, in fact, what is the thickness of the semiconductor device? Actual semiconductor device thickness is hardly 5 to 10 micron, whereas your wafer thickness is 700 to 1000 micron thickness. In that one, only top 10 micron is semiconductor device. Functionality of the device is limited to top 5 to 10 micron. All rest of the area, rest of the volume is just a empty this one. And the size of the structures, it has few nanometer to few micron scale. And critical thing is there are multi layers in the device. The number of layers varies from 20 to 200. So it is very important in positioning these layers and structures very accurately. That is the challenge in semiconductor device fabrication. That is where the lithography and etching plays very critical role. So if you look into, as a layman, if you want to understand what is semiconductor device, it has array of structures of different shape, different dimensions, and it is multi-layers. The number of layers varies up to even 200 or 20, 50 like that. And the dimensions of structures, they are in the scale of nanometer, submicron, and micron scale. For example, today you want to see what is the thickness of a gate oxide, it is all 1 nanometer. 1 atomic layer or 2 atomic layer. We need to control in that scale actually. This is to understand how a semiconductor device look at if you look into the cross-sectional layer, silicon wafer. See what you see in the bottom, you see so many transistor, resistor, all the active elements. I said there are only 4 elements: diode, transistor, resistor, capacitor. All are at the bottom. These are all the, you can see bottom, mostly this one. This is the what we call gate level or transistor level. So all your billions of components, active elements are present at the bottom. Above that, we see memory level. It is optional. Not all the devices are having memory. Some devices like DRAM, SRAM, they have memory, microprocessor chips and all built-in memories. So it is in the middle actually. Then top level, which is known as contact loop or a metal loop, it has a multiple layers of metal, which is the one making connection from one element to the another one. So it is responsible. The number of metal layer, it varies. For simple devices, it can be 1, 2, 3. Nowadays, it has exceeded 10 in some devices. So that means this whole structure is not more than 5 to 10 micron. So if you have a wafer of thickness 700 micron or 1000 micron, only top 5 or 10 micron consist your active device. Rest of the thing is only bare silicon. As you can see, there are very, very critical structures. You can see memory cell, which is very closely spaced actually. They should not cross, they should not short, or they should not break. Similarly, you have gate oxide, which is very thin. So accurate positioning of the structures, creation of the structure is very critical. And we are going to see what are the key processes and challenges in these processes. So major fabrication process, it involves mask plus lithography. Etch means removal of the material. These are the two we are going to discuss in detail in today's presentation. And of course, thin film deposition. We need to add some new material where only silicon is present. And there are other supporting process like doping, which means we need to add impurities in a controlled way. Cleaning, though it looks very simple, very challenging, but because we need to clean nanostructures and we need to remove the contamination without damaging the structures. And chemical mechanical polishing. So this rapid thermal processing, these are all some of the supporting processes. Testing is of course at the end. So the key process which repeats many times is lithography. What is the lithography? I need to define the space. That means I want to make some capacitor. I want to make some transistor. First, if I must define where exactly it has to be put in the wafer. That definition of space, technically we call as a patterning. That is the purpose of lithography. Then etching. Etching means I need to remove controlled removal of materials of micron scale, submicron scale. Then deposition means I need to add some new material in that hole. So these are all the 3 important processes which repeat several times, while making the devices. Whole device fabrication cycle takes 2 months, 3 months like that. But this process repeats dozens of times, depending upon the which IC we are going to fabricate. As I said, we are talking about few nanometer, submicron, critical positioning. Even a misalignment of few nanometer, either it can become short or it become open. It becomes, basically non-functional. And we need to etch deep vertical trenches. And we need to deposit micron and submicron scale thin films in these wires. These are all the challenges which is becoming more and more difficult. When we had a 20 micron technology, it was quite bigger. Error of 1 or 2 micron does not affect. But now we are moving to the nanometer technology. Error of 0.1 micron means it is a huge. So it is unacceptable. Now, first we start with lithography. Lithography is what is the smallest structure that we can print on the wafer? That is the question. Because earlier, when we were using 20 micron technology, the transistor size used to be 40 micron. But today we are talking 10 nanometer, 5 nanometer, 2 nanometer. So how we can print such a small structures without creating any problem, without creating any short, without creating any open? That is the challenge when we are talking about nanometer technology. Resolution, that means what is the smallest difference between one structure to other we can create. And added to that, throughput, because it is a business, manufacturing. In industry, we typically process 2,000 wafers per day, 2,000 wafers. Otherwise, wafer cannot survive economically because it has a $5 billion investment. So we have to get back. So throughput, all this process has to be optimized to have so many output. So what is the first step is pattern transfer. Lithography means I need to transfer the pattern on the wafer. Where is this pattern is generated? So it is generated in VLSI design. It is the design people who will tell what are all the connections required between various elements. Which transistor has to be connected to which capacitor has to be connected to which diode to be connected to resistor, like that. All the connections are defined by circuit design people. That file is known as GDS. So you might have familiar graphical design system. Once the GDS is made, that is a graphical. So that graphical has to be translated to a physical one. That is the mask making. Whatever the design you have got in the GDS, that has to be translated to a mask. It is a template on the thin glass sheet actually. This itself is a very, very complicated and big complicated system. It will print the GDS structures, GDS map onto the glass. Then this, whatever this pattern is there, we cannot directly transfer to the silicon. We need to transfer to the photoresist. From this photoresist, we are going to transfer to the silicon dioxide. From silicon oxide, we are going to transfer to the silicon. Ultimately, I need a structures, well-defined structure on silicon, but this cannot be done directly. There are various important steps. So next couple of slides, you understand how it is done. So this is the one circuit design is given by GDS. From GDS, how we are going to print the same structure on the silicon wafer. So I will show you with some few simple symbolic pictures. So this is the important steps in lithography. So you have got a wafer here actually. Then we have got a resist application, photoresist. It will undergo some soft baking. Then we have got to align and expose. This is the light coming actually. Wherever the photoresist is there, it gets softened or hardened depending on its type. Again, we have to bake it. Then develop. Develop means wherever photoresist is soft, it dissolves. Then we do metrology. Metrology means whether the pattern we got is same what we wanted, how much is the deviation. That means the pattern is now transferred to the photoresist. From photoresist, again we transfer to the silicon dioxide, from there to silicon. So you can see it actually. This is the wafer. We spin coat. That means we put few drops of photoresist and rotate to few thousand, it will spread uniformly. Then we heat it. Then this is a critical process. Exposure light. When we expose with light, photo means light. It is a light sensitive polymer. Wherever light falls, its chemical property changes. Either it becomes soft or hard, depending upon the type of photoresist. Then we post develop and remove the exposure of photoresist, we get the pattern. So this is one you can pictorially see. It has a light source is there actually. There is a reticle. It is the pattern is there actually. It will flow to the different. It will print and stage will be step and repeating. So basically, what it has, it is a illumination system. That means optical source. There's a reticle. That is the pattern. Then exposure system where exposure time, energy, everything is controlled. Wafer is here, which steps to the different this one. This is called step and repeat. Now, the trend is how we are able to get smallest feature. So the resolution is determined by wavelength. So you know resolution R is equal to lambda divided by numerical aperture. So if I want to get better, smaller feature, the only way is to improve the or reduce the wavelength. That has been happening. If you see it actually, we have been reducing the wavelength of the light to various. This one. So this is helping to have smaller size of the pattern to be printed. So we started with G line, mercury arc, I line, krypton fluoride, argon fluoride, fluorine, extended UV, etc. And today there is no choice. We have been using electron beam lithography. Why electron beam lithography? The smallest wavelength we can control only by electron. You know, de Broglie principle. Electron also behaves like a wave, and the wavelength is determined by momentum. That means larger the momentum, velocity, wavelength will be small. Velocity depends on energy. So by increasing energy of acceleration, we can have smaller wavelength. That is the electron beam lithography is the latest one we have been using. What is mask? It is an optical filter. So whatever the design is there, the design file is transformed to the silicon using this mask. It has a region of opaque and transparent. So wherever it is transparent, light will pass through. Wherever it is opaque, light will not pass through. It is the purpose of mask. That means your design pattern is first printed on the mask. Now, when we expose actually, it is not that we expose single die, we expose couple of die at a time. This is called reticle. When we say it is 2 by 2 reticle, it exposes 2 by 2. That means 4 die at a time. When we say 3 by 4 reticle, it exposes 12 die. When I say 3 by 3 reticle, it exposes 9 die. Because exposure is not limited to one die. At a time, we expose 4, 6, 9, etc. This is known as reticle. And you can see reticles. And this is the mask. Wherever mask is the transparent, light will pass through. Other region, light does not pass through. So we have two types of exposure system. One is step and repeat. Another is step and scan. This is the latest one. It scans continuously. This has very high resolution advantages compared to step and repeat. We don't go into the details of that one. But for your information, one scanner costs nearly $300 million. 300. And we need at least 1 dozen of scanner to meet the throughput of 2,000 wafers per day. So this is the typical wafer fab, how it is done. Lithography. Now, how do we transfer the pattern from mask to the silicon? As I said, it is not a single step process. It has multiple steps. This is the starting material silicon. I cannot transfer the pattern directly from photoresist to the silicon. The first step what I am going to do is I deposit silicon dioxide. So on the silicon, I deposit a thin layer of silicon dioxide. This dioxide, I'm going to remove it later on. That means it does not have any performance in the device. Therefore, it did not be very good quality. So generally we use wet oxide for growing this one, which is very fast and low cost. Once I deposit silicon dioxide, typically 1 to 2 micron. Then I deposit photoresist, which is also typically 1 or 2 micron. So I want to create a pattern, but I cannot directly create. Therefore, I'm depositing silicon dioxide. Then after that, I'm depositing photoresist. Once photoresist is ready, I am exposing through the mask. So these are all the masks. So when I expose it to light, light is blocked in certain region and light is transmitted and reaches the photoresist. Wherever there are transparent regions, light pass through and interacts with photoresist. As I said, the name photoresist means it is a chemical, it is an organic chemical, it is sensitive to the light. Photo means light. So wherever light is interacted with this material, it becomes very soft for negative photoresist. Oh, sorry, positive resist. So in this region, it becomes very soft. So now photoresist is exposed, it has reacted. Wherever light is exposed, it becomes soft. Other region, it remains hard. After that, what I do, I remove the soft photoresist by using chemical. So what happens? Photoresist only in this region get removed. Other region, it remains. So after that one, I get this one. This is the photoresist. Wherever light is exposed, photoresist is because it is soft, removed. So by doing this, what I have done, the pattern which was in the mask has been transferred to the photoresist. That is what I have done. So this photoresist is quite hard material. Now what I am doing, using this one, I am removing silicon dioxide using chemicals. Chemical means certain plasma etching. So now wherever photoresist is there, it is blocking the silicon dioxide. Therefore, wherever photoresist is not there, it is allowing silicon dioxide to be etched. Therefore, from this structure, I am etching silicon dioxide so that wherever photoresist is not there, it will etch in the direction. So when I do that one, I am getting in a structure. See, silicon dioxide is etched wherever photoresist is not there. Is it not? So I get a structure like this. Now, the purpose of photoresist is done. It is over. So I'm going to remove the photoresist. So when I remove the photoresist, I get this structure. So now I got a silicon over that patterned silicon dioxide. That means I transfer the pattern from mask to the photoresist. Now photoresist to the silicon dioxide. Now what I'm going to do, I am etching the silicon. Now wherever silicon dioxide is there, it will black. I am using certain plasma ions. So wherever silicon dioxide is not there, it will etch. So when I etch the silicon in this condition, only silicon which is present where oxide is not there is going to etch. So that is what the pattern I'm going to see. Now silicon is etched only in certain this location. So now the job of silicon dioxide is done. So I'm going to remove the silicon dioxide again by chemical etching. So this is the pattern. You remember I had the pattern at the mask. From mask I transferred to the photoresist. From photoresist I transferred to the silicon dioxide. From silicon dioxide I transferred to the silicon. This is the structure pattern I'm going to get. Of course, pictorially I have shown very big. These structures has to be few nanometer, submicron scale actually. That is the challenge. So how do you precisely place these structures very, very close and very, very sharp actually, deep? This is the challenge we are having. So wafer photoresist is coated actually. There are various problems. So suppose this is the mask pattern actually. When I print it on photoresist, I do not get exactly this one. I get distorted images like this. So there are, as I said, there are two types of photoresist. One is positive, another is negative. If I use positive photoresist, wherever light passes through, there I get a hole. Remaining area, it looks solid. On the other hand, same mask. If I use negative photoresist, wherever light passes through, I get a pillars like this. All remaining area material is removed. So I can get either this structure or this structure just by changing the type of resist, whether I use positive resist or negative resist. Now, questions of challenge. Is it everything is okay? Whatever the pattern I have on the mask, can I get it? That is not the real situation. Suppose I have a pattern like this. When I put it like this, I get a distorted images. Corner gets round, lines get shortened, overlay error, CD error, it bends actually. So when I print it, actually, there are so many errors will be there, deviations. So how do we counter this one? How do we solve? This is the challenges of lithography. And when we go to the micron scale, sub-micron scale, nanometer scale, it challenges becomes much, much severe. So you can see, if you design the mask pattern like that, when you print it, this is the actual structure you are going to get it on the wafer. See, this is not the one we wanted. We wanted this one. Now people have worked reverse engineering. That means I want to get this structure. What should be the mask shape? That is called optical proximity corrections. This itself is a very interesting and open research area. So to get this kind of structure, I must use a mask like this. So this will compensate various errors and print like this. So now I have a desired pattern. What should be the shape of the mask? So that is called optical proximity correction. And there are a lot of research going on for different geometry, different shapes and all. And also when you have layers like this, actually, there is a reflection away from two sides, surface and bottom. They can have an interference. And because of interference effect, you will see wavy kind of structures. You can see when we do lithography and etching. So how do we minimize this one? How do we minimize the standing wave effect? These are all the challenges we are having. And what is the smallest feature we can print? That is decided by the resolution, which is K, it is some system constant depending upon the equipment. Lambda is the wavelength, is numerical aperture. That is why there is a tendency we have seen in reduction of the wavelength. We have tried different sources of the wavelength, different light sources. And today we have reached all optical sources have exhausted. We have come to the electron beam, because in electron beam, I can control the wavelength by controlling the energy. So that is the only choice we are having in it is in the nanometer scale. And numerical aperture depends on refractive index and the angle of collection angle. Collection angle, it is not possible to increase beyond 90 degrees theoretical limit. Therefore, typically we use 45, 60 degree. And refractive index is the one thing we have this scope. And 45 nanometer technology and below, we have been gone to the immersion lithography. That means there is a whole media is immersed in the water, whole optical system. So because water refractive index is nearly 1.33, therefore it will improve the resolution by 30%. So this is the latest technology, 45 nanometer and all, immersion lithography. Whole optics, it is a liquid is flowing and it is immersed actually. But there are many challenges. The water flow should not create any challenge. You should not any turbulence. You should not have any contamination and block the transmission of light. It's not easy. It is just it looks like a theoretical, but it has been implemented for 45 nanometer and below, because it gives an improvement of 33% improvement in the refractive index and the resolution. So these are all the challenges we are having. So there is a lot of still scope when we go to the micron scale, sub-micron scale, nanometer scale. How do we get the distortion-less pattern getting transferred to the wafer? The pattern what we are having is in the mask. How to get the same pattern on the photoresist? How to replicate same thing on the silicon dioxide? How to replicate the same thing on the silicon? At various stages, distortion take place, and we have to minimize. And there are a lot of scope for R&D and opportunities of different light sources, different optic systems, different process optimization. So this is the one aspect of lithography. Once we have the pattern, actually, the second critical process which comes is etching. What is the meaning of etching? Etching stands for removal of material. Removal means I need to remove the material so that I can add new material. Because you have seen the silicon device, it has various new material. It has aluminum, it has copper, it has silicon oxide, silicon nitride, it has memory cells, different material. So polysilicon, there are so many new materials are there. How I can add unless I remove it? Therefore, I need to remove the material in a controlled manner in the control locations. That is the purpose of etching. And it is important etch rate because productivity is important. I cannot take few hours or few days to etch it. Selectivity is very important. That means I want to etch silicon, but I should not etch the adjacent silicon dioxide. I want to etch silicon dioxide. I should not damage the adjacent silicon nitride. Like that, we have a lot of constraints. Selectivity means I want to etch one material without damaging or without etching the other material. So how best I can do? Then etch damage. Today, most of the etching is done by plasma. Plasma means it is energetic ion beam. This ion beam should not add impurities, should not add ions getting trapped in the device and create later on circuit problems. Etch damage, what is the tolerance we are having? And etch profile. In some application, I am going to show you, we need deep etch with 90°. In some application, we need tapered etch. So how do you control the etch profile? So these are all some of the important challenges and important requirements. So I'm going to explain what is the role of etching in device fabrication. When we say etching can be done in ambient condition. That means atmosphere in some application. Etching also happens in vacuum and different types of plasma etching system. And I'm going to show you two case studies, which was done first time in the world by me in Singapore, long back. So it is already more than 20 years, but I will briefly tell how critical it was. And also to show you ion beam assisted etching and some R&D opportunities in this one. So as I said, now you can see these are all the structures. I need to make this kind of vertical etches. The diameter or size of these vias are typically 0.2 micron, 0.3 micron, and depth is few micron. How do I etch this kind of vertical holes without disturbing the adjacent structure? It looks simple. See, because I am using plasma. Plasma means ions. See, when I use ions, where I am injecting the plasma, where plasma is created, it is created at the surface. I am injecting the gases at the surface, and because of ionization or a field, it get ionized. But what is the probability these ions go inside? Because if they do not go inside, they cannot etch. So what is the probability these ions get moving to the inside? That is the one biggest challenge. When these wires are very thin, like 0.2, 0.5 micron. Even if I assume there are some few ions which goes inside and reacts, it will generate byproduct. Then what is the probability this byproduct comes out? If this byproduct does not comes out, they get stay, then my whole purpose is defeated. So removal of the byproduct is equal or more challenging in etching. Therefore, I need to optimize so many parameters and make sure that enough ions go inside etches and these byproducts are volatile and they come out. These two criteria has to be met, which is very, very difficult and very challenging. So as I said, etching happens in ambient and certain process happens in vacuum. We'll briefly review what kind of process that takes place in ambient and what kind of process that requires vacuum. So very simple. One is mechanical polishing. You can remove the material by just polishing in a controlled manner. And wet etching, it also happens in a, and laser. Many of the laser you don't need vacuum, you can use in the atmosphere. So if you do mechanical polishing, it is good enough just to remove the material. It has very poor selectivity. It does not bother whether it is silicon oxide or silicon nitride. It just removes whatever it comes on the way. So very poor selectivity. Therefore, it is useful only when selectivity is not at all criteria. You just need to thin the sample by few micron. It is okay. It is low cost. It is difficult to control thickness. Therefore, one has to use proper gauges and keep on watching in between. Of course, it is a low cost and most of the time it is manual. In some equipment, it is semi-automatic operation. That means you can set the thickness. You can set the thickness 5 micron, 10 micron. There is a gauge. It will stop after removing 5 micron. and it is non-localized. That means whole device or whole paper, it will do it. And it generates a lot of particle contamination. That is one of the biggest challenge in device fabrication. Removal of contamination or avoiding contamination is a requirement. Therefore, it is not used for device fabrication. However, it supports some other activities in device like testing or anything. So CMP is slightly added version of polishing. Here we add some chemical pad so that with selectivity, it removes silicon nitride more compared to silicon oxide. Like that it is. So it has a different chemical pads. By using different chemical pads, I can remove one material preferentially compared to the other. That means it has a better selectivity compared to the polishing. It's basically polishing, but I have chemical pads in this one. So I can choose different chemical pad so that it can remove either aluminum, it can remove silicon nitride, silicon oxide. Differential etching is possible. So again, it uses slurry. In fact, if you look into the 1980s and 1990s, it was considered as one of the dirtiest process. It was banned. You can see 200 research paper on CMP. It was banned. But again, it has been reinvented. There is no permanent friends or enemy in semiconductor. Today, it is one of the unavoidable process. We need it actually. Similarly, if you look into the research paper during 1980, copper was banned. You can see 200 research paper on copper-induced damage, copper-induced degradation and device failure. You can see it was banned. People have stopped using copper. But today, without copper, you cannot do it actually. Again, it has been reinvented by solving so many problems. That means things will come and go. They take different forms. Therefore, CMP was banned earlier. It has been again reinvented with lot of improvement. Similarly, copper was banned. Again, it has been reinvented. So this kind of things keeps on happening in device technology. So wet means it is a liquid, chemical, basically. So advantage is very, very low cost. The biggest advantage is high selectivity. That means I want to etch silicon dioxide, but not silicon nitride. I can choose a proper chemical. I want to etch aluminum, but not silicon dioxide. I can choose a chemical. So chemicals provide very high selectivity. So selectivity is the criteria. This is the best method available and low cost. The problem is poor profile control. It etches in all the directions. So you cannot have profile only vertically. Isotropic means all direction it etches. Therefore, some application isotropic is acceptable. Definitely, it is the best thing to go for wet etch because low cost. Another problem is safety concerns because we are using some of the dangerous chemicals. We need to be very, very careful. We need to practice all the safety chemicals. For example, when we use acid like sulfuric acid, nitric acid, one drop falls on my skin, it burns. Immediately go and wash with water. But some chemical like HF, I don't feel anything. It looks like a cold, but it will get into your bone and damage your bone. So we don't even feel it. So these are all the lot of safety concerns, lot of training is required. Then because lot of chemicals we are using, we should use proper humid and exhaust and train the people. In fact, however training we give, there will be some accident. In our own fab, we had a problem. We are supposed to put acid waste into one bucket and alkaline waste. But some new operator, he mixed it somewhere, he put wrong place. And that was lunchtime, everybody went to lunch. By the time we come, it got fire. So already, of course, there is a fire alarm, people will come and extinguish. But this kind of mistake happens actually. So safety, training, safety concerns are very important. Then laser assisted etching. This is also ambient because most of the laser they pass through the atmosphere, no problem. But it is localized. That means you want to etch certain specific part of the material of few micron size. It is not for whole wafer. It is a localized and material sensitive to wavelength. So different materials they absorb lasers of one particular wavelength. Therefore, it is possible to etch maybe silicon oxide, but not silicon nitride. This kind of selectivity is possible by choosing proper wavelength. There are very parameters are there. We need to optimize pulse width, pulse repetition rate, laser power, beam mode. There are so many. Again, it is new throughput is very low because I cannot use it for whole wafer. It takes very long time. It is some specific purpose only I can do it. Maybe at the time of R&D, you want to fine tune some process or do some changes and do it. It is okay. It is not for production purpose. Now, when you come to the vacuum conditions, under vacuum condition, what are all the steps we can do it? How? Broadly speaking, there are two techniques. One is called plasma assisted etch. Another is called ion beam assisted etch. In plasma assisted etch, the vacuum level is relatively low. But when you go to the ion beam assisted etch, it is very high vacuum. Again, plasma assisted etch, very high throughput. Therefore, it is used in manufacturing production purpose. Whereas ion beam assisted etch is throughput is very low. It is used for some device modification or some trial run, some experiment. It is not for throughput actually, manufacturing. Therefore, but we'll cover how plasma assisted etch work and how ion beam assisted etch is useful. So this is a comparison. So wet etch is directionality is isotropic. When you come to the plasma etch, it is anisotropic. That means I can etch in one particular direction. Selectivity, wet etch provides very high. It is low to medium. This is a selection we need to optimize the process. But here profile control is true because it etches in all the direction. Here it is possible to have very good control and sometimes even 90-degree profile, which is required. As I shown, it is possible only in plasma etching. Now compared to the cost, it is very, very low. Any R&D lab can have it by few lakhs, but it is all in the crores. So that is the difference. Any small experiment, R&D institute, academic institute, definitely we prefer to do with wet etch, but if it is manufacturing their production high end, definitely plasma etch is the choice. So this is plasma etching. There are different types, plasma assisted etching. By the way, what is plasma? I believe all of you know, it is a fourth state of matter. So when we hit solid, like ice, it becomes water, liquid. If you further hit water, it becomes vapor, that is gas. If I provide further energy to the vapor, what happens? Even electron gets separated from the molecule. So that is called a plasma. It is an ionized state. So even electron is no more remaining with its parent atoms. Selectivity. What is the meaning of selectivity? Have different materials, maybe silicon, silicon dioxide, silicon nitride. When I put chemicals, how differently it etches different material. Does it etch silicon more than silicon nitride or more than silicon nitride? This is selectivity. This is very important. How the chemistry we have chosen etches one particular material and not other. This becomes very important. So it is a fourth state of matter. It contains electrons, ions, and neutral atoms, and it has to be generated. So typical parameter, it has a RF diode configuration, high density plasma. Typically, the vacuum is in the range of millitorr actually, and the power, it varies from 50 to 5,000 watts. Then frequency, operating frequency. So there are certain allocated frequency. I cannot choose any frequency of my choice. For industrial application, there are certain allocated frequency. Only that frequency we have to choose it. Then volume, typically for production purpose, these are good enough. And we need to, sometimes we need to apply magnetic field to confine the plasma. And plasma density, you say plasma density because we are using vacuum. These are all the typical number of particles per cc. And the electron temperature gives the energy of the electron using electron volt. By the way, you must know what is the meaning of 1 electron volt. 1 electron volt, see, you can generate 1 electron volt just by giving 1 volts to the energy electron. But if we want to provide same energy by heating, it is around 11,000 degrees centigrade. So if thermally it is not possible to provide that much of energy. If you provide 1 electron volt by thermally means everything melt and evaporate 11,000 degrees centigrade. Therefore, you must imagine these figures looks very simple, but 1 electron volt, if you calculate temperature equivalent, it is around 11,000 degrees. So by thermally heating, it is impossible to give that kind of energy. But here we are providing energy of that kind actually. Then ion bombardment energy, how much we are providing, and fractional ionization. The whole gas is not ionized, some fraction is ionized. So how the plasma works actually? I generate the plasma. That means ionize the gas by applying RF field or DC field. So there are ions. What happens actually? Ions has free electron. For example, this electron collides with CF4, carbon tetrafluoride. What happens? It becomes CF3, fluorine, and electron. So now fluorine is very reactive with silicon. So silicon reacts with fluorine, forms silicon tetrafluoride, and it is volatile and is gaseous. This is very, very important. The byproduct must be volatile. It cannot be liquid or solid. If it is solid, it will stay on the sample. I have to remove the byproduct. Otherwise, it will block the next reactions. So it is important to choose the chemistry such that it reacts with my sample, silicon, and not only that, the byproduct is volatile. If this condition fails, my whole purpose is defeated. Therefore, selection of the chemistry is important here actually. So typically, the selectivity of 1 to H silicon typically should be more than 100 we need. That means if we H 100 micron silicon, hardly 1 micron should H in silicon dioxide. That is the meaning of selectivity. Non-uniformity. Of course, I have 18 dia wafer, I have 12 dia wafer. I want everywhere H rate should be uniform. But theoretically or practically, it is not possible because plasma density itself is not uniform. If you have studied the plasma, you have seen it actually. Plasma itself try to repel each other. So they try to move out. At the edge, density will be more. At the center, it is less. Therefore, plasma density is not uniform. Therefore, there are many other reasons. Therefore, it is difficult to achieve better than 5%, but still 5% is somewhat acceptable. Another thing is contamination. I have engineered the gases. There are so many particles are there. You should not deposit on my wafer. So there is a restriction or limitation on the contamination which get deposited on my sample. So it should be less than 10 to the power of 11. Then because here energetic ions are bombarding, I have a gate. Gate means transistor structures. So that also get absorbed some of the ions. And when ion is absorbed by transistor, its threshold voltage will shift. So there is a restriction on the threshold voltage deviation. You should not drift by more than 50 millivolt. And similarly, gate leakage current should not increase by more than 0.1 nanometer. So these are all the requirements or constraints I am having while optimizing various parameters. There are various types of plasma system. Plasma means I need to ionize the gas. So there are different combinations. One is RIE, which stands for reactive ion etching. And reactive ion etching, I can have magnetic confinement so that my density will be more. ICP, I can have inductively coupled plasma. Another is deep reactive ion etching. This is very, very important if I want to do MEMS and structures and all. Sometimes I need to create a via for holes of 100 micron, 200 micron. It is not possible by simple RIE. For that, deep, as the name suggests, is deep RIE, deep structures I can create. And nowadays we are using even microwave reactive ion system. It has some more advantages and limitations. So you can see typical system, how it looks actually. This is the chamber, which is completely in vacuum actually. It has two electrodes, top and bottom actually, and it has it is not shown. It has a RF generator, which has so many control systems which can control. There are so many mass flow controller. We can inject. There are 6 to 8 types of gases we can inject through the mass flow controller. Then we can control the pressure. We can control the impedance matching network is there. All these things are not showing. Only operator has the controller. He can set and we can see the status, which valve is open, whether RF is on or not. Everything he can see it. So it is an anode and cathode. It is a 2 electrode system. Vacuum chamber. Typically, we operate 10 to the power of -1, -2 torque, typical range. And we need to have a gate valve. So sometimes we need to control the flow of the gases. Okay. Mass flow controller is very important. We use different gases. The flow rate is very important. We need to control very precisely. If it is 50 SCCM, it should be 50 SCCM. 60 means 60. So very precise control of the flow is one of the important parameter in controlling the H rate and other parameters. And as I said, there are different configurations. We can have a DC plasma system, RF, radio frequency, microwave, etc. And one of the important things is impedance matching network. What is the impedance matching network? If I use RF field or if I use microwave generator, there is a reflection of the power. And that reflection of the power should be compensated and well adjusted. If reflection is more than the limit, then or it is fluctuating, then I completely lose control on the process. Therefore, it is a built-in impedance matching network is one of the key requirements. So we need to have an impedance matching so that reflected power is less than whatever the set, maybe 10%, 15%. So this is a part of the system. Then load law. So sometimes we keep the sample, then after in the semi-vacuum, then we put into the chamber. This is a load law. It is required in some high volume operation. And this is very important. Endpoint monitoring system. Suppose I am removing silicon and I must know all the silicon is removed. How do I know how much time I have to etch? So there should be a way to monitor and say complete silicon has gone. Or I want to remove silicon dioxide, but not aluminum. So there should be a way to monitor endpoint detection. So most of the plasma etching system, they come with endpoint monitoring system for different materials. And some of them requires backside cooling. So to avoid the rise in the temperature of the cathode and maintain the uniform etch rate. These are all the system configuration. It is not necessary you need all of them to be present in a given system. You can manage without endpoint monitoring system. If your structure is very simple, you want to etch only silicon, by trial and error, you know how many minutes it will go. So we can manage, but production purpose, it is not acceptable because everything has to be automated. So when we say how to etch, actually, there are two things actually. One is physical sputtering. These ions are energetic coming. They bombard and transfer physical momentum to the molecules of interest. So this is called physical, and that molecules get operated. So this mechanism has poor selectivity. It does not bother whether the ion is hitting silicon or silicon dioxide or silicon nitride or aluminum. It provides energy and removes whatever is there. But it is highly directional because ions are accelerated in one direction. Chemical etching. Here it is chemical reaction take place. Therefore, it is very selective, high selectivity, but it is bit isotropic. Therefore, in plasma chamber, we use the parameter, we combine such a way that I want high directionality, at the time high selectivity. So I cannot have pure physical sputtering. If it is pure physical sputtering, my selectivity I lose. If it is pure chemical etching, directionality will become high direction. Therefore, I need to take advantage of both these mechanisms. So the parameter, process parameter I am selecting should be such that it has as high directionality, that means physical sputtering, and as high selectivity as chemical. This two combination is very important depending upon my structures. So this is all the challenges of process optimization, parameter selection. So we need to etch various materials. I want to etch silicon, silicon dioxide, silicon nitride, silicon, doped, undoped, N-type, aluminum, molybdenum. There are so many compounds. So we have already tried so many chemicals, and these are all some of the established chemicals which have shown good results. It does not mean it is the end. It is an open research. One can work with new kinds of chemicals which may probably give better kind of selectivity, better kind of etch rate. So you can do, it is an open research, but these are all some of the standard agents today industry is using, but it is not limited. Once again, itself, there is a wide scope or opportunity available to try with different kinds of chemicals and see how I can get better etch rate, how I can get better profile control, how I can have lesser damage, lesser contamination. So improvement is always open. So one can try different chemistry. So as I said, these are all the kinds of structures. We have vertical structure, which is very, very challenging to etch actually. See, you have such a deep, the width diameter is 0.2 micron, whereas this depth is something like 5 micron. How to create this kind of structure? As I said, there are two challenges. What is the probability my ions will go inside these deep trenches? Why they will go? Why they need to go? They are ions, they are gases. They move by themselves. There is no preferential reason for gas molecules to come here. There is no specific reasons. And even assuming some molecules comes here, actually, they react, they generate the byproduct. What is the guarantee these byproducts will come out and escape? There is no reason. They can stay here. They can stick into this one. This is a quite challenging when we want to have deep trenches. It is not easy. I'll tell you once again. In industry, the person who knows etching this kind of deep trenches and lithography, they are really highly in demand in the whole world actually. It looks very simple, but it is very challenging. The slight mistune, you lose everything. So there are important steps in plasma etching. First of all, the radicals are generated in the plasma. That means ions, due to the bombardment of the electron, these electrons are in the chamber. And these radicals, they have to diffuse and transport to the radicals, and they should move towards the sample. Otherwise, you generate the radical. If they don't move and come to the sample, no use. So it has to come to the sample. Sample is very small area compared to the whole chamber. Chamber is like a meter cube, whereas your sample is very, very small. So what is the probability these molecules will reach the sample? That is the one big thing. And not only that, they come, they can just touch and go. It is some no use. It's just like a giving shake hand or saying hi. It does no use. It does not serve any purpose. They have to get absorbed on the surface. Otherwise, no use. If they simply come and meet and go. And these absorbed species, they have to react with surface and form a product. This one, they have to get dissolved. That means it reacts and the byproduct remains with the wafer. It is again another headache. So instead of removing, I'm adding some more contamination. So that is why selection of chemistry is very, very challenging. It requires all these things. Desorption of the byproduct is very, very important. And they should diffuse and go back to the gases. Remember, at the one end, I have a gas injection. Gas is injected at one end of the chamber. Another end, there is a big, vacuum pump. It is trying to suck whatever it comes on the way. Therefore, when I put it, it should not go to the vacuum pump without interacting with my sample. It should go to the sample, create certain radicals that should react, and byproduct only should go to the vacuum. If the injected gas directly goes to the vacuum, my purpose is defeated. That is why selection of the chamber configuration, where you inject the gas, where you keep the sample, where you put the vacuum suction, all these things are very important. How much time it goes. Therefore, any misalignment or mistuning means you will not get the sample, you will not see any etching. So this will pictorially show you are generating the etchant, you are injecting the gases. That the gases should move to the sample. If it moves directly to the vacuum, it is of no use. There is a vacuum pump remaining. You are injecting the gases through mass flow controller. One end there is a vacuum pump. So vacuum pump is sucking whatever it comes. Therefore, you should not get sucked to the vacuum pump. You should move to the surface. So what is the probability? How many molecules out of 100 will reach the surface? That is one question. Second is, once it comes and touches the surface, it should not simply go. It should get absorbed. What is the probability? Suppose 10 molecules get absorbed by the surface. Then once it gets absorbed, it has to react with the sample, chemical reaction. Once it reacts, it has to the byproduct, it should get dissolved. If byproduct is not dissolved, if it is staying, it is another headache. These byproducts should be sucked by the vacuum pump, not the injected chemical reactions. So how I cannot control, I cannot tell vacuum pump, you suck only byproduct, not the injected gas. They won't bother, they won't listen to me. But it is a selection of the process matter, positioning of my injection of the chemicals, positioning of my vacuum, and there are so many process parameters. It looks simple, but not easy. Then I want to etch silicon or I want to etch aluminum, different material. How do I know where to stop? How do I know? So there are, one is R&D. If it is for small experiment, you don't need to you take after 5 minutes and see whether still silicon has gone, aluminum has gone. That is for R&D. Production purpose, I need a automated actually. We use so many spectroscopic methods, optical emission spectroscopy, secondary electron spectroscopy, impedance monitor. Once, for example, I want to use silicon, next layer is silicon dioxide, there is a different reflection. Therefore, by using optical spectrum, emission spectroscopy, or self-excited resonance spectroscopy or impedance monitoring, I can know, oh, silicon is etched. There is a sudden change in the spectrum or sudden change in the impedance. So these are all some of the tools we use it. Therefore, it knows automatically, it stops everything actually. It is connected. Therefore, most of the production purpose equipment, they have a plasma monitoring tool. It is optional, but most of the time it is essential. If it is R&D or some product development, we can manage without this one. But when you go from manufacturing, there is no human intervention. They monitor the spectra automatically closes, stops. So plasma monitoring tool. Again, there are a lot of opportunity. We have plasma monitoring tool is available, some of the chemicals. So now so many new chemicals are coming, new gases are coming. The R&D and academic institute can work what kind of spectrum it is useful for detection. So it is still open-ended. As I said, when we have a plasma etch mechanism, it has a chemical reaction and it has a physical bombardment. And physical bombardment has a directionality but poor selectivity. Chemical reaction has a poor directionality but good selectivity. So it is a selection of the process parameter to choose which one has to dominate. You want to have more chemical reaction oriented etch or sputtering etch, it depends your process parameter. If you take more ion energy, definitely sputtering will be more. Then chemical reaction effect will be less. So you can optimize the process parameter. So what are the requirement? As I said, etch rate is important from manufacturing point. So typically, I should finish it off in few minutes. It is not worth to take few hours. Productivity will affect. Selectivity is important. I want to use silicon, but not silicon dioxide. I want to use aluminum, but not silicon. Like that, we have a different combination of selectivity. Etch profile. Most of the cases, we want vertical as possible. And particle contamination. My whole process should not generate too much of contamination that degrades the device performance. And process parameter. So if I may be using RF or microwave, power is very important. Distance between anode and cathode that affects the device process performance. Gas flow rate, not only gas flow rate, where do we put the gas? Where do we inject? Gas injection should not be very near to the vacuum suck point. Then my whole purpose is defeated. Whatever the gas I inject, it will go to the vacuum. It will not even come to the specimen. Impedance mismatch is important. Too much of impedance mismatch, there will be a lot of heat dissipation. Some cases we heat the sample to have a proper processing. So the substrate temperature also becomes important. Etch rate means thickness of layer, how much microns we remove per minute. And too high etch rate means it becomes difficult to control. Production wise, it is good, you make fast, but controllability becomes difficult. Too low means manufacturing yield will reduce. So we generally optimize the one micron per minute is somewhat a reasonable rate for manufacturing. So there are different types of plasma. You can have DC plasma, RF plasma. If you have a DC plasma, it is not good for insulator, it is good for conducting. RF plasma, it is both for insulator and conductor working. ICP, inductively coupled plasma, we have high energy, high density, and microwave, some specific material, they are very good for microwave plasma. So it is just a configuration. You have a RF generator, you have anode, cathode, and plasma is generated. You're injecting the gas and you are sucking. This is very important. Where you inject the gas, you should not put sucking point here close to this one. Then whole purpose is defeated. So now I am showing two case studies which are very, very important. These were the work done more than 20 years, but at that time it was highly challenging actually. And I had the opportunity. This was the first time we developed this technology in the world. And because it was a manufacturing industry, They did not allow to patent or anything. That is industry policies actually, but it was quite challenging. I will show you what is the meaning of IBC, how we were successful in finding the IBC and how it helped the production and detection of cell to cell shock. So both of them requires very precise combination of wet touch and dry edge. So what is the meaning of IBC? IBC stands for insufficient buried contact. It is one of the unique failure signature in semiconductor devices, particularly in memory. But electrically, when this failure signature comes, it is very difficult to confirm what is the reason actually. So we need to understand what is IBC. All the semiconductor devices, they use polyplug. In fact, all your structures are sitting on the polyplug. So whether it is your memory cells or some other tungsten contact, they are sitting. It provides electrical contact for many of the functional plugs. And it provides structural support for the many of the functional plugs. And to have a good contact, we use a term called dimple edge so that it makes very good contact with silicon substrate. For example, this one. Yeah, this is a structure. You can see there are so many polyplugs here actually. On this polyplug, memory cell is standing. On this polyplug, memory cell is standing. On this polyplug, you are seeing tungsten is standing. It provides support for various structures actually. But the question is whether this polyplug is making good contact with silicon substrate. That itself can be a major problem. How do you know that these polyplugs are making good contact when all the structures are fabricated? How do I know? That is the biggest challenge. So that technology I developed actually. This is the finished wafer. That means I have a fully completed wafer. Now I am seeing some electrical signature which suspects some problem in polyplug. But I need to confirm. How do I confirm this polyplug connectivity with silicon substrate when it is fully fabricated? That is insufficient buried contact. So what is the meaning of insufficient buried contact? This is my polyplug and this is my silicon substrate. To have a sufficient good electrical contact, this polyplug should penetrate 2 nanometer so that it provides electrical contact. This is the example of a good contact. But if I go that one, it is a marginal contact. It is working, but it can create problem. And sometimes it can have a poor contact. It is some thin layer of oxide, still some partial contact. It is not acceptable. This kind of problem is there, which this was unnoticed until we manufacture. But how do we determine this kind of problem and confirm that this problem has occurred? That is the one I have done. So this is my finished wafer. Therefore, I need to go down to this level and see whether polyplug have made a good contact or not. So it was very memory cell. The oxide thickness is typically 0.2 micron. So when I etch it, I have to retain that oxide. Cell height is 3 to 5 micron. It requires very deep etches with such a narrow gaps. And I need very high selectivity. If we calculate, typically selectivity desirable is 100, more than 100. That means I want to etch silicon, but not damage the oxide wall thickness. So these are all various challenges we had actually. And we did not have a very expensive system like ICP, ECR, or because their maintenance cost is very high. We did not have certain high selectivity chemicals because it was not used because of their hazardness. And whatever the method I tried was retain the oxide wall. That is very important. Even though it is 0.2 micron oxide thickness, I should make sure that it does not get damaged, and controlled removal of tungsten silicide there, and controlled etching of the memory cell is required, cell plate. Then each memory cell I have to remove, and I have to etch the polyplug. Then I can see whether it had made a good contact or not. And I need to check the impression. Like that, with a small coconut plant, whether it was seeded properly or not, if you lift it, you can see its impression below the ground. If it is not put enough, it is on the top of the mud, it will come out, it does not leave impression. It is similarly, I am seeing the impression by doing all this work. So it requires controlled etching of the memory cell, controlled etching of the polyplug. So I have done a lot of calculation and come to the conclusion that in my system, I have to use as low power as possible. It was 600 watt RIE system we had, but I went below 40 watt, the plasma started triggering, flickering, so it is not stable. Therefore, I cannot go below 40 watt. So I found that somewhat 60 watt, I get low and stable RF power actually. Then operating pressure, I did some calculation to the chamber and worked out around 100 to 120 millitorr. Then edge time cannot be too large again for industry purpose. So somewhere 12 to 15 minutes was acceptable. And overedge also problem, it will damage the impression. So I need to make sure that it is not overedge polyplug. So this is the memory cell. This is a polyplug. I need to remove this one. This is silicon. This is silicon. This is silicon. This is silicon. This is substrate is also silicon. I need to remove this polyplug without damaging this substrate and see the impression. So all are silicon. How do we remove this selectively, this silicon, but not this? This was quite challenging. So all these problems we addressed actually. Then when we etch completely, see this is the impression that will tell that it had enough penetration and made a good penetration. When you have good kind of impression like that, my polyplug is good. But if you go to the failed device, you can see poor impression. That means this is the one impression is poor. That means contact was marginal. That was creating damage. So this was a very interesting technology we developed 20 years back, and it was widely used in our industries. So another technology was cell-to-cell talk. You see, if you said 512 MB DRAM, there are 512 millions of cells. So these cells are very, very close. If there is any short between them, it will have electrical failure signature. And dimension of the size is typically 10 mm by 10 mm. In this one, there are 512 billions of cells. So how do we identify short between two cells? So it was very big challenging. So this is what you see, polyplate covering this cell. So there is this all polysilicon plate, very thick. You have to remove it in a controlled manner. So then we did so many experiments. These are all the memory cell. When I say memory cell, for example, data 1, it is stored in memory cell DRAM. What is that DRAM? This is the cylindrical structure. These are all the way data 1 or 0 stored. These are all like that. There are 512 million memory cells are there. So I can see every individual cells, and now you can see there is a short between these two cells. So we were successfully able to see short between two cells in a very effective manner. This for the technology I developed, of course, 20 years back, but it was quite challenging and good. Like that, there are hundreds of requirements in the industry. We have so many challenges, we have so many opportunities to work on etching. So this is for plasma etching system. It is widely used. So there is another system which is called ion beam assisted etch. When I say ion beam assisted etch, it is a very complex system, very expensive system. It is very slow process, low throughput, and very skilled job. It requires a lot of skill, but advantage is highly localized. Sometimes you don't want to yet remove the material throughout the silicon chip. You want to remove in one selected point. You want to remove maybe 1 micron, 0.5 micron. So therefore, that kind of application, that kind of failure analysis, fault detection, fault confirmation, it is used. It is not used for manufacturing. Once again, remember, it is highly localized. Plasma etching is global. That means whole wafer it etches. It does not discriminate any location. It is very fast. Wafer, 25, we can put wafer by wafer in a wafer. Very fast actually. This is very low throughput because here we are etching at one particular location, maybe 1 micron, 2 micron like that. Therefore, it is useful only in some troubleshooting purpose, not for manufacturing. So it is a very expensive system. If you look into the system configuration, it has a ion source, ion column, and vacuum because we need a vacuum for electron ion. Then detector we need to get the image. Again, it uses different gases, gas delivery system, and stage is there, very precise control, process control. So this is a typical system. You won't see anything here actually. You have a ion column, everything is there actually. Then this is where sample is loaded actually. You can focus the ion wherever you want, and you can etch the material where you want. That means it is not etching the complete device, complete wafer. No, it is localized, highly localized to the submicron scale. It is very expensive system. Those days it was more than 10 crore. Now definitely it has gone more than 20 crore, I believe. So this is the system. We have a focused ion beam system. It is supported by infrared for imaging. Gas assisted etching. It uses different gases to etch nitride, to etch silicon, etc. And I can position the beam or I can position the stage very accurately using laser guided stage. And it has a navigation tool. If you have a GDS map, you can load it and tell which coordinate it will go to that position of very sub-nanometer scale precision. So pictorially, you can say there is a focused ion beam coming here. It is your device. I am injecting certain chemicals through micro nozzles, tiny nozzles to the particular point. Actually, I control the stage so that wherever I need to go to the structure, I go to that particular position and remove the material. Yes, it is not for global, it is for atomic scale. So important features are it has a laser guided stage movement. Therefore, stage precisioning is like a submicron. It has a CAD navigation through night software. It has a gas assisted etch. We use different gases for etching silicon, silicon nitride, silicon oxide, aluminum, etc. It has a IR microscope. Sometimes we can do backside etching using IR microscope. We can do both front side and backside modification. So the main thing is it has a gallium, liquid gallium ion source. These ions are accelerated, focused, and made to fall on the specimen. So typical ion energy varies from 30 to 50 kiloelectron volt. So there are various parameters to choose pixel size, pixel spacing, dwell time, refresh time, nozzle spacing, nozzle temperature. All of them we need to optimize for a given process. So here we take the chip. We don't etch or remove the material everywhere. We take the chip. It is basically used for circuit modification. So it is important that wire bonds are integrated. There is no damage to the wire bond. Then I go to the device location particular. I remove the passivation layer. I am seeing the metal layer here, aluminum metal. Now I want to etch metal in a submicron scale. I want to break this connection for some reason to verify the impact on device performance or verify whether it is a fault causing the device performance. So I go to the metal layer, which is very wide actually, you can see. Now I want to make a break. That means some 0.5 micron I want to cut it. So I use this ion beam to cut it. You can see this one. For this kind of special application, we use ion beam. It is not for production purpose. It is mainly for device functionality verification. Sometimes we have a design itself, something is wrong. This metal line was not supposed to be connected. That is why giving trouble. Now I verify, I break the connection and verify the device performance. Then I give feedback to the designer. So this is very, submicron scale etching. Similarly, I can create via. See, when I say device, it has multiple layers. Sometimes you have top layer, sometimes you can go to bottom layer and do the edit thing. You can cut the material. And in fact, you can add the metal also, that's different. But I can create via structure so that I can access different layers which are below the top surface. So I can create via of different shapes and access. So this is the very important for micron scale, but this is not for production purpose. So we must have a precise location where we want to do this kind of modification, removal of the material. For that, we use laser assisted stage and CAD assisted navigation. So we can mill or etch to submicron or micron features. In fact, we can deposit also. That is another application that does not come to under the category of etching. We can add conducting material. We can add inducting material. So this is basically called microsurgery. So it can create 3D submicron structures. So a lot of application. It is works, though it is 10 crore, but this is a etching in vacuum and but highly localized, and it is not for a production purpose. Now, the main theme of this workshop is AAML, role of AAML. So I prefer to call as MLAI. That means first machine has to learn, then only it is it can do the AI. So what are the opportunities? So if you come to the lithography, there are thousands of distortions of different pattern image printing. I want to print different patterns. I have thousands of distortion. We need to understand those distortions. There are thousands of deformation in profile due to etching. When I etch, I don't get vertical, sometimes different slope, different kinds of etching. And I do not know what is the distortion in the image printing. I do not know what kind of deviation has occurred, deformation occurred. Finally, what do you see? Millions of deviation in electrical signatures. So there is a leakage current decrease, leakage current increase, threshold voltage drift, some performance degradation, temperature instability. There are so many that we see only every device is performed. There are millions of transistors, billions of transistors. Each transistor, there are dozens of structures responsible for that one. So how do I can correlate? How do we collect and huge database is there? How do we collect these data? How do we have a learning so that my machine can correct and automatically? If my device is some degradation is there, is it due to this step? There are lithography, there are dozens of steps. Etching, there are dozens of steps. Which step it has caused the problem? Can we correlate? So understanding specific signatures and automated corrective action, this is the biggest challenge in industry. So when we say wafer fab, finally we see the deviation at the end, not in between. Therefore, but in between, in 2 months or 3 months, there are 200 steps it has undergone. How do we correlate these kinds of deviation and see? So this is the learning. So how do we understand the signature? How do we correlate it to different this one? It is a huge opportunity. This is the what I want to say. It is an open-ended research actually. So large database, we have a petabase data in wafer fab. Every process, every operator, every machine, everything is recorded. Pattern recognition, very important. Image processing, that important. And I prefer to call as MLEAA, though AML is common term. Machine has to learn. Then only we can implement the AI algorithm for process automation. Then ultimately, we need to control the defect and deviation. So these are all the huge opportunities. Therefore, I believe, we can, students and faculties can think in different direction of solving the problem. Any small contribution also welcome in industry. So I would be glad to answer any specific questions or.
We now invite participants to pose their questions for our speaker in the chat box.
A few selected questions have been taken up for discussion to ensure an engaging and interactive session.
Sir, actually, there are a few questions in the chat box.
Yeah, please.
So one question is, sir, in my 3 years of experience, I was thinking plasma etching and ion beam etching were same. Am I thinking in the correct direction?
Plasma is a ion, definitely. Plasma is ion, therefore it is ion beam etching. Both are used in interchangeable way.
And so there's one more question, that if the etching step leaves the surface of the transistor slightly rough, does that increase electron leakage? And can we use a specific deposition technique to fill in those microscopic scratches and make the transistor more energy efficient?
It is partially right. It is not fully understood. When we have etching, it is not going to be vertical. When we do lithography, I cannot print the same structures, but how it affects the device performance, it is a open end. Certain areas we have seen that leakage current increases if scope wall is not 90° and all, but it is not fully understood for all the devices, all the geometries. It is the open research. How a transistor works differs at 10 micron technology is entirely different when you come to the 10 nanometer technology. The impact of structural deviation on a transistor, it depends on the technology node. Some 10 micron technology, it may not impact, but when you come to the 10 nanometer, it becomes very crucial. So it is again open area and lot of scope for understanding and correcting.
And so there's a follow-up question to the first question, but you mentioned some vacuum change between plasma and ion etching. So it's a follow-up to
Ion
the
etching
first
or ion beam
question
etching?
about
Ion etching or ion beam etching?
Sir, the question states ion etching, but I think it means ion beam etching.
Ion beam. Definitely ion beam
Ion
etching.
beam etching,
The
sir.
main,
Ion beam
yeah,
etching.
ion beam etching vacuum levels are quite high because we have to accelerate the ions to 30 kilovolts, 50 kilovolts. Therefore, they have to be in high vacuum condition, like 10 to the power of -6. But when you do plasma etching, we are generating the ions in a different way, not by acceleration. We are generating the plasma. Their energy levels are relatively low. Therefore, we don't need that kind of high energy.
So there's one more question. Sir, what does the directionality, anisotropy, and isotropic mean actually?
Isotropic means it etches in all the directions equally. Suppose I put some chemical, allow it to etch, the profile will be almost like a 45-degree because it etching horizontally and vertically equally. If I etch it for 1 minute or 2 minutes, I get a profile somewhat like 45-degree. Anisotropic means it touches ideally 90-degree. That means it creates a whole structures vertically. That is isotropic. Anisotropic. Isotropic means it touches in all the directions.
Sir, I think
If anyone has more questions, they can share in the chat box. And also, feedback form is being provided. Please fill it out so that we can enhance our future ATAL FTPs.
sir, there is one more question.
Please.
We were taught like all base layers were wet etched, and all metal layers were plasma etched. And is that
No,
true?
no, that is wrong. That is wrong. Because plasma metal also can be etched by wet etch. It is a requirement. Whether you want to see, as I said, if you want high selectivity, wet etch is a better choice. But you want profile control or you want to, other requirement, you don't want to have less contamination, then we have to go for plasma etch.
And so
Any
one more
material can
question.
be etched by
Yes,
wet
yes.
also. Whether it's silicon dioxide, silicon nitride, aluminum, copper, we can etch it by wet.
And so there's one more question. In
Please.
high precision micro nano fabrication, how
Yeah.
do we ensure the reliability of ML models when the process data distribution drifts over time due to tool aging or environmental variations?
It is a very good question. The good thing is we have a record of each and everything. Suppose I say, if you want to look into the wafer fab really, if you take, for example, plasma etching system, when the whole vacuum chamber was cleaned last time. So when it is due for cleaning, when the electrodes are taken out and cleaned, every record is there. When the mass flow controllers are cleaned, every data will be there actually. So the probability, suppose it is cleaned today and it due for next 15 days. So after 10 days, if there is a degradation performance, it is something it is due for the maintenance problem. Like that, all the data are available. That is the one of the biggest advantage, and the data size peta byte actually. And not only that, each process we have a SPC, statistical process control distribution. So that chart gives you a lot of indication on the stability of the process. And every operator is monitored. We have a complete history. The wafer might have processed even 1 year back. I can check which process it has been done, which operator has done, which equipment. Everything we can verify.
And sir, one more question. What sort
Yeah.
of topics can be introduced for BTech as part of fabrication and instrumentation at which year?
See, microelectronic engineering is a one branch actually. Some of the MTech people also it is there actually. It involves all this process. That means lithography, deposition, etching, then CMP. All these fabrication process are there one semester. It is a good course. Whole fabrication is a one cycle. You can put it either for BTech or MTech.
And all right, sir. I think so you have answered all the questions. So thank you, sir, for sharing such a wealth of knowledge drawn
Welcome.
from decades of hands-on experience in semiconductor fabrication
You
and
are
nano
welcome. You can
manufacturing.
contact me anytime also.
Thank you, sir. Thank you.
Session provided invaluable insights into clean room practices, advanced equipment, and real world implementation of semiconductor technologies, greatly benefiting faculty members and researchers. And now I would like to request all the participants to fill out the feedback form in case anybody is left or they haven't filled out. So your feedback is crucial to for enhancing the future ATAL FTP.
We sincerely thank our esteemed speakers and all participants for making day one a successful and enriching experience. We look forward to your continued participation in the upcoming sessions. Thank you and have a wonderful evening. Sir, if you wish to leave, you can.
Okay, thank you. Thank you.
Thank you, sir. Thank
Pooja
you.
ma'am, you are on mute.
Acha,
Okay,
yes, ma'am.
okay. Thank you, Ramachandra sir. Thank you so much. Has he left?
Yes, ma'am. I'm sorry, ma'am. I didn't know that you were about to.
Okay, okay, okay. No worries.
I'm very sorry, ma'am. I didn't know that.
Okay, okay.
I didn't pay
Okay.
attention.
No worries, Shiva. Okay, thank you everyone. Have a nice day ahead tomorrow. Okay.
Thank you. सेशन एंड नहीं करना ना हमें those who haven't filled the feedback form can please do so.